Imagine if construction could be not just strong, but ultra lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from a 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in saltwater. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation, a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal.
Every year in the world, only 21 mysterious B-2 Spirit aircraft are created, genuine ghosts of the sky. Its length is almost that of a multi-story building, whilst its wingspan is greater than a football pitch. But the main intrigue lies in the materials. Composites, titanium, and aluminum alloys make it lightweight, yet incredibly strong and almost invisible to radars. Radio waves become lost in the layers. Paint absorbs signals, and engines hide their thermal signature like a shadow in the night sky. This isn't simply an aircraft, it's an engineering myth about which legends have circulated for decades. Watch until the end, and you'll learn a secret not shown even in military archives. Everything begins with material selection, and here the B-2 Spirit is truly extraordinary. For its body, they don't use ordinary metal as in old aircraft, but take composites, titanium, and aluminum alloys. Composites are multi-layered sandwiches of fibers and resins that are lighter than steel yet significantly stronger. It's precisely thanks to these materials that the aircraft not only withstands colossal loads, but also remains almost invisible to radars. Radio waves simply become lost in the composite layers without reflecting back. Imagine, the B-2's length is almost 69 feet, whilst its wingspan exceeds 171 feet. It's like a football pitch, only instead of grass, there's black stealth gliding across the sky. The empty weight of the B-2 is over 71 tons, whilst maximum takeoff mass reaches 171,000 kilograms. But even with such dimensions, it appears elegant because its shape is pure aerodynamics. No superfluous protrusions, everything smooth as in nature. Every detail is manufactured with jeweler's precision. Titanium and aluminum are used where special strength is needed, for instance in engine mounting points or undercarriage. And composites cover nearly the entire surface. They're responsible for stealth and lightness. Incidentally, special body coating not only absorbs radio waves, but protects the aircraft from extreme temperatures at altitudes exceeding 50,000 feet. Next follows multi-stage processing, grinding, quality control, application of special layers. Every millimeter is checked with laser scanners, so there's not a crack nor the slightest gap. Here, everything is at high technology level. Robots and people work together, creating a genuine work of engineering art. It's precisely thanks to these materials and technologies that the B-2 Spirit can fly thousands of miles, remaining invisible both to radars and thermal imagers. In the B-2 Spirit, nothing is accidental. Every curve of the fuselage, every wing line is the result of thousands of hours of calculations and tests. Engineers literally draw the aircraft in air so that it doesn't simply fly but merges with the sky. It's precisely thanks to this shape that the B-2 looks so futuristic. It's as though created not to challenge the air, but to become part of it. Every detail, even the slightest protrusion, is calculated on supercomputers. Imagine, even rivets and joints on the body are hidden so as not to create unnecessary reflections for radars. And there's also a secret weapon here: special paint. This isn't simply a black matte layer, but a multi-component coating that absorbs radio waves and doesn't allow them to reflect back. That's precisely why even powerful radars see the B-2 as a tiny dot or don't notice it at all in the sky. Assembly of the B-2 Spirit is a genuine engineering performance that occurs in enormous workshops accessible only to chosen few. Here reigns an atmosphere of maximum secrecy. People and robots work together like a single team. Robots lift and hold massive sections whilst engineers manually install the tiniest details. The aircraft body is assembled piece by piece like a gigantic three-dimensional puzzle, where every element must fit perfectly in its place. All joints are checked with lasers. This looks like a scene from a science fiction film. Enormous cranes, laser scanners, people in special clothing, robots moving with incredible precision. Every day in these workshops is another step towards creating an aircraft that changes the rules of the game in the aviation world. Next, engines enter the stage, the genuine heart of the B-2 Spirit. Designers hide engines inside the body rather than placing them outside as in most aircraft. Thanks to such integration, the B-2 appears maximally smooth, and this also helps hide thermal traces. The whole trick is in the exhausts. Hot gases that are usually clearly visible to infrared sensors here pass through special long channels. In these channels, gases cool, mix with cold air, and only afterwards exit outside. Therefore, even modern thermal imagers see the B-2 as a barely noticeable shadow in the sky. The aircraft cockpit is isolated, protected from noise and light, comfortable even during many-hour flights. Next, onto this foundation are applied layers of insulation so that inside it's always quiet and comfortable even if engines roar outside. The feeling is as though you're in a capsule that screens you from the entire world. Now, in the cockpit center are installed two seats. They stand side by side like in a modern sports car. Seats are soft but strong with numerous adjustments. Before is an enormous digital screen. All controls are to hand. Touchscreen panels, joysticks, buttons with different textures so they're easy to find even by touch. Around are panels with instruments. They don't protrude, but smoothly transition one into another like waves. A folding rest area, a folding bed, space for food, even a small toilet. This is space where one can relax whilst one's partner holds the controls. Everything is made so that crew can remain focused and not tire even during flights lasting over a day. When the cockpit is ready, it's covered with special coating that protects from temperature fluctuations, from bitter frosts to heat. All joints are sealed so there's not a single draft or extraneous noise.
What if the most dangerous part of a suspension bridge isn't what you see? Because inside the main cables, which look like solid metal, there's a structure made of tens of thousands of wires, each one vulnerable to destruction by even a drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can see it? The Golden Gate Bridge in San Francisco has two main cables, each about 37 inches in diameter. Inside each one, 27,572 individual wires. If you unwound all these wires and connected them into one line, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one of these cables? Around 24,500 tons. That's comparable to the mass of a small cruise ship. Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made of many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of kilometers. Stay till the end. You'll learn a secret that even bridge engineers don't talk about. Picture the classic example, San Francisco's Golden Gate Bridge. It's got two main cables draped over towers and anchored into massive concrete blocks in the rock. Each cable's about 37 inches across. That's not a cable anymore. It's practically a pillar you'd need 2 or 3 people to wrap their arms around. Inside, 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and link them end to end, and you've got roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. One cable weighs around 24,500 tons, comparable to a small cruise ship or several hundred fully loaded semis. Why so many wires instead of one giant solid rod? Steel handles tension beautifully, but it doesn't tolerate flaws well, especially in large cross-sections. When a cable is made up of thousands of individual wires, each one can give a little, taking on a bigger share of the load in some spots, a smaller share in others. If one wire happens to corrode or weaken for some reason, its contribution to the overall strength is minimal, and you won't even notice it in how the whole cable behaves. Plus, it's way easier to create a flexible shape out of tens of thousands of thin elements. A cable can smoothly wrap around towers, forming a big parabola across the span, whereas a solid rod of that diameter just can't be bent without permanent deformation. The process of making the main cables for a suspension bridge is nothing like how regular steel cables are made at a factory. Nobody ships a pre-made coil a yard thick and thousands of feet long to the construction site. A monster like that would be impossible to deliver or lift into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary working cables between the towers. They run a traveling cart along them that can zip back and forth across the entire span. The cart carries a coil of steel wire. Each trip of the cart means threading another wire between the shores. One end of the wire gets fixed to an anchor on one side. The cart hauls the coil across the span. The wire gets secured on the other shore, and the excess gets cut off. Then the next wire, and so on, tens of thousands of times. To keep this insane marathon from turning into chaos, the wires get organized into what are called strands or subcables. For example, several hundred parallel wires get bundled into one strand of a specific diameter. First, all the wires get tensioned with a little slack. Then special jacks even out the tension so each little wire carries roughly the same load. Then the bundle gets clamped with rings or special bands to keep it from spreading apart. When there are enough of these bundles, they get brought together and compressed again into a single cylindrical structure. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold incredible force. Picture a bridge deck suspended from it. a steel truss or box girder carrying the road surface. This deck structure transfers the load to the main cables through suspenders. Any vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or multiple trucks together. Wind pushes against the side of the structure with a force that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally just a few inches along their entire length while staying within the elastic range. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The modulus of elasticity and tensile strength of these cables are specifically chosen so that working stresses stay well below ultimate limits, even accounting for wind gusts, temperature swings, and heavy traffic flow. During the design phase, engineers model every possible loading scenario. Both lanes completely filled with trucks, sudden braking, seismic events. The result? An acceptable range of cable elongation and sag within which the bridge remains safe and comfortable for users. Here's the fascinating part. Despite all that rigidity, the main cables aren't absolutely static. They breathe with the bridge. On a hot sunny day, the steel expands and the cables sag slightly. At night, as temperatures drop, tension increases and sag decreases. In windy weather, you might notice a gentle oscillation in the deck. The cables themselves are actually moving too, though it's invisible to the naked eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters in bridge building history, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic: protecting cables from corrosion. Steel fears moisture and salty fog, especially in coastal regions like San Francisco. If water and aggressive contaminants get inside a cable, reaching each of the tens of thousands of individual wires, corrosion can silently eat away the cross-section for years until it's too late. That's why immediately after strand spinning and compacting are finished, cables get sealed. First thoroughly painted, then the coating is periodically refreshed. Modern bridges employ additional systems: wrapping with airtight tapes, filling gaps with dehumidified air or nitrogen, monitoring humidity inside. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods, which allow engineers to understand the condition of the wires without opening up the cable. All of this is done so that a single strand of infrastructure can safely serve for decades. The cables of the Golden Gate were designed for a service life of tens of years, but thanks to proper maintenance, regular repainting, and monitoring, they still do their job today, holding up the main span of over 4,000 feet. If you add in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire stretched across rivers, bays, and straits, keeping millions of cars suspended in the air every single day. Using main cables made from thousands of steel wires is standard practice for large suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge across the Hudson in New York. It also has two main cables woven from tens of thousands of steel wires. The total length of all that wire is measured in thousands of miles, and the mass of each cable runs into tens of thousands of tons, just like the Golden Gate. The same technology was used on the Brooklyn Bridge, though it's older and combines a suspension system with cable stays. There, the main cables also consist of a large number of thin wires spun on-site rather than brought in as pre-made rope. modern giants are built using the same principle. For example, Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made from many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of miles, and the design tension reaches hundreds of thousands of tons. A similar approach is used on numerous bridges in China and South Korea, which have been actively building long-span crossings over bays and wide rivers in recent decades. All these bridges share one technology. The main cables are spun on-site from tens of thousands of individual wires, each one tensioned, aligned, and compressed into a unified structure. This technology creates cables of incredible strength and flexibility, capable of holding thousands of tons and handling dynamic loads from wind, traffic, and temperature changes. And so, traveling from a coil of steel wire through tens of thousands of trolley trips across the void, through hydraulic jack tensioning and compression into bundles, through wrapping with protective wire and coating with anti-corrosion paint, the main cable of a suspension bridge is born, a structure of 27,572 individual wires, weighing 24,500 tons, able to stretch several inches under load but staying within elastic deformation, holding in the air a bridge over 4,000 feet long, carrying millions of vehicles every single day. Each wire is a separate element, and if one weakens, it's barely noticeable to the whole system. But if moisture and salt get inside, corrosion can silently destroy wires for years. That's exactly why modern bridges are equipped with humidity monitoring systems, regular inspections, and non-destructive testing. So these giants of steel and concrete can safely serve humanity for centuries.
There's a metal so rare that humanity mines less of it in an entire year than it does gold in a single day. A metal that costs anywhere from $4,000 to $9,000 per kilogram. A metal you've probably never heard of, yet right now, it's keeping the plane you flew on for vacation from falling out of the sky. This is rhenium, the rarest stable element in Earth's crust. A silvery white metal that doesn't exist as a standalone ore and is only extracted as a byproduct. Without it, there would be no modern jet engines, and aviation would be stuck at mid-20th century levels. Let's start with the scale of rarity. Rhenium makes up about 7/1000ths of a part per million in the Earth's crust. For comparison, gold is 4/1000ths, platinum is 5/1000ths. The numbers seem comparable, but there's a fundamental difference. Gold and platinum can be found as nuggets or concentrated ores. Nature sometimes gathers them in one place. Rhenium is never found that way. It's scattered as microscopic impurities in other ores, mainly molybdenum and copper. The concentration is so low that even calling it rhenium ore is incorrect. It's always ore of something else that happens to contain rhenium. Rhenium itself looks like a silvery white metal with a slight grayish tint. But most people have never seen pure rhenium. Even in industry, it's more often used as alloys or powder. In nature, rhenium occurs in just one mineral, jacasganite, which is so rare it literally exists in only a few places on the planet and has no industrial significance. All industrial rhenium comes as a byproduct of processing molybdenum concentrates, which themselves are a byproduct of copper mining. A byproduct of a byproduct. That's what rhenium is. Think about the scale here. To get just 1 kilogram of rhenium, you need to process roughly 200,000 tons of copper ore. 200,000 tons of rock for a single kilogram of metal. It's like searching for a needle, not in a haystack, but in an entire field planted with hay. The main sources of rhenium are molybdenum mines in Chile, the US, Kazakhstan, and Armenia. Chile dominates, about 50% of global production. The Chuquicamata mine in the Atacama Desert is one of the largest open-pit mines on the planet, where they extract copper and molybdenum, pulling out rhenium along the way. The pit is so massive you can see it from space, roughly 2¾ miles long, nearly 2 miles wide, and over 3,000 feet deep. Extracting rhenium is complex and multi-staged. First, copper ore gets mined and enriched through flotation to produce copper concentrate. That concentrate contains molybdenum, which also gets enriched and separated out. Molybdenum concentrate is molybdenum sulfide with microscopic traces of rhenium, typically 0.05 to 0.2%. Sounds convoluted, but it's essentially a chain: copper ore to molybdenum concentrate to rhenium solution. At each stage, volume drops by factors of thousands, while value skyrockets. The molybdenum concentrate gets roasted in special furnaces at around 1,100 degrees Fahrenheit and higher in open air. Molybdenum oxidizes to trioxide, which can then be reduced back to metal. But rhenium behaves differently. It oxidizes to rhenium heptoxide, which vaporizes at this temperature and escapes with the gases. Those gases pass through a complex system of scrubbers, towers where they're washed with water or alkaline solutions. Rhenium heptoxide dissolves, forming rhenic acid or perinates. Rhenium concentration in these solutions is tiny, grams per liter, but that's something you can work with. The solution is purified of molybdenum, copper, lead, and other metal impurities through multi-stage chemical treatment: extraction, ion exchange, precipitation. Then rhenium is precipitated as a white crystalline powder, ammonium perrhenate. This is the most common form of rhenium feedstock for further processing. To obtain metallic rhenium, the powder is heated in a stream of hydrogen at temperatures exceeding 1,800 degrees Fahrenheit. Hydrogen reduces the rhenium oxide to pure metal. The result is rhenium powder, which can then be sintered, melted, or used directly in alloy production. Each year, humanity produces about 50 tons of rhenium. 50 tons! That's the entire global output. For comparison, about 3,000 tons of gold are mined annually. Copper, 20 million tons. Rhenium is so rare that global reserves at any given moment are measured in hundreds of tons, not thousands or millions. Here's the question: why mine something this rare in the first place? The answer? Jet engines. About 80% of all rhenium goes to the aviation industry for making superalloys that form turbine blades. A jet engine turbine blade operates in absolute hell. Gas temperatures hit 2,700 degrees Fahrenheit. That's above the melting point of the alloy the blade is made from. So it's cooled from the inside by airflow through microchannels. The pressure is colossal. The blade spins at tens of thousands of revolutions per minute, experiencing monstrous centrifugal loads. A corrosive environment with sulfur impurities from jet fuel. And all of this for years of continuous operation with zero margin for error. Because if a blade cracks mid-flight, the engine destroys itself. Nickel-based superalloys, the primary material for blades, contain nickel, chromium, cobalt, tungsten, molybdenum, aluminum, titanium. But even these incredibly complex alloys couldn't withstand high temperatures for extended periods, until they added rhenium. Rhenium does something remarkable. It dissolves into the nickel matrix of a superalloy and blocks defect movement in the crystal structure at high temperatures. This is called creep, the gradual deformation of metal under load when heated. All metals creep, but rhenium slows this process down dramatically. Adding just 3% rhenium to a nickel superalloy raises the operating temperature by about 54 degrees Fahrenheit. Doesn't sound like much? But in jet engines, every 18 degrees of additional temperature yields roughly 1% more efficiency. And efficiency means fuel consumption, flight range, airline economics. Modern superalloys contain up to 6% rhenium. A single turbine blade can hold anywhere from 5 to 20 grams of rhenium. One engine on a large passenger jet, about 13 pounds of rhenium in the blades alone. 13 pounds of metal worth up to $50,000 in a single engine. And a plane has 2 engines. Every year, thousands of jet engines are manufactured. Passenger, cargo, military, and virtually all the rhenium mined goes straight into them. Because of its rarity and high cost, the industry is desperately trying to reduce rhenium consumption. New generations of superalloys with lower content are being developed, along with the use of ruthenium, an element from the same group that could theoretically replace rhenium. But ruthenium is even rarer and more expensive, so for now, it's just research. Single crystal blade technology makes rhenium work smarter. Instead of a regular polycrystalline structure, each blade is grown as one massive crystal with no grain boundaries, which are weak spots at high temperatures. This lets you cut down on rhenium content while keeping performance. But the process is complex and expensive. Each blade is grown individually in specialized vacuum furnaces with extremely slow, controlled cooling that takes hours. Recycling rhenium from spent blades is mission critical. After thousands of hours in hellish conditions, blades wear out and get replaced. The old ones don't get tossed, they're melted down, rhenium and other precious metals extracted and used again. Around 30% of rhenium comes from recycling, more than most other metals. And the reason's simple. At these prices, nobody can afford to throw rhenium away. The remaining 20% of rhenium is used in other areas. Platinum rhenium catalysts and oil refining to boost gasoline octane ratings, filaments for mass spectrometers and electron microscopes, anode materials for X-ray tubes. The strategic importance of rhenium is enormous. Countries without access to rhenium cannot produce modern jet engines. And this isn't just a matter of civil aviation, but military, fighters, bombers, cruise missiles. Interestingly, rhenium was one of the last stable elements to be discovered. German chemists found it in 1925 while examining platinum ore through spectral analysis. They named it after the Rhine. Before that, Mendeleev had predicted the existence of element number 75, but no one could find it because of its extreme rarity. Basically, the entire world's supply of this metal would fit in a few trucks, and the whole world's aviation depends on those few trucks.
Every year, the world produces over 1 billion new tires, and just as many worn-out ones end up in landfills. Just imagine, in the United States alone, over 250 million tires are recycled annually, saving the planet from mountains of rubbish. But where do these black rings go after they've served their thousands of miles? They don't simply vanish. They pass through fire, steel, and grinding machines to be born a second time. And what's most captivating, we don't even realize that every day we walk on their second life. Stay till the end, because there I'll reveal a secret that will forever change your perception of an ordinary tire. So today, we're heading to a cemetery of automobile tires. Hectares of land buried under mountains of black rubber rings. These are the silent veterans of the roads, which have rolled their thousands of miles and now lie here, seemingly useless to anyone. But this isn't the end of their story. It's merely the beginning of their remarkable reincarnation. We'll trace how these worn, dirty chunks of rubber pass through a series of brutal yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. Americans have learned to give a second life to the overwhelming majority of tires. The recycling rate for old tires in the U.S. currently exceeds 85%. This means that over 250 million tires annually avoid landfill and are sent for rebirth. Part of them are burnt as highly efficient fuel. Part are used in civil engineering, but a significant and ever-growing quantity is transformed into rubber crumb. At this tire graveyard operates a machine resembling a steel tyrannosaurus. It's an industrial shredder. An enormous loader grabs an entire handful of old tires and tosses them into the steel jaws of this machine. Inside it, with a deafening screech, two massive shafts with thick, sharp hooks rotate. They seize the tires with relentless force and tear them to pieces with an incredible crash. Inside every tire is a steel belt, a robust framework of steel wire. During tearing, this belt is released, transforming into a glittering web of steel threads mixed with rubber chunks. This chaotic mixture of rubber and steel moves further along the conveyor. And here, an industrial, powerful, enormous magnet enters the game, rotating above the stream of shredded material. Like a fridge magnet, but a million times stronger. It extracts all the steel threads from the rubber mass. With grinding and clanging, the steel belt sticks to the magnet and is dumped into a separate container. This steel will then be sent for remelting, whilst our purified rubber continues its journey. But it's still too large. Next stop, the granulator. During this process, another tire component is released, textile cord. These are nylon or polyester fibers that gave the tire additional strength. These light, fluffy fibers need removing. For this, rubber granules pass through a system of vibrating sieves and air separators. Powerful air streams literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have clean but still rather large material. To become stadium surfacing, it needs transforming into crumb. For this, granules are sent for final grinding, often in so-called cracker mills. As a result of this process, we finally obtain what everything started for, rubber crumb. This is a uniform, free-flowing mass resembling black caviar or coarse sand, where each particle size is just a few millimeters. This crumb is carefully sieved to guarantee perfect size uniformity and packed into enormous bags weighing a ton each. Its journey from dirty tire to clean, high-tech raw material is complete. And now, let's transport ourselves to where this black crumb will find its true calling, construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. But for now, they look dreary and lifeless, pressed against the base. For them to stand up and resemble real grass, they need support. And here, a special machine enters the pitch, resembling a large fertilizer spreader. A process called infill begins. First, the machine spreads an even layer of fine, rounded quartz sand across the entire pitch. It's heavy and settles at the very base of the carpet, acting as ballast so the turf doesn't shift. And following the sand, our main hero is poured onto the pitch, black rubber crumb. The machine distributes it just as evenly across the entire surface. And here, the main transformation occurs. It's like running on a billion tiny trampolines. This dramatically reduces the load on athletes' joints and makes falls far safer. The final touch is combing the pitch. A special machine with an enormous brush drives across the turf, carefully mixing sand and rubber crumb and combing them deep down to the very base, forcing every blade of grass to stand perfectly upright. And now, when the work's complete, before us appears a perfectly green, springy, and safe pitch. And none of the players running on it might guess that beneath their feet lie millions of particles from old automobile tires. To create one standard pitch for American football or soccer requires on average between 20,000 and 40,000 old car tires. Just think about it. A single pitch completely devours an entire mountain of rubber waste. And how many such pitches are there in the country? Currently in the U.S., there are over 13,000 artificial turf pitches in schools, colleges, parks, and professional arenas. And now simple maths. If we take even the minimum figure of 20,000 tires per pitch, it turns out that in sports pitch surfacing across the country alone, over 260 million old tires have found their new home. Natural turf is a very finicky thing. It needs constant mowing, watering, fertilizing, and giving it rest. On average, a natural pitch can withstand no more than 20 hours of play per week. And a pitch with artificial turf? It can operate 24 hours a day, 7 days a week, in rain and heat. And now about water. One artificial turf pitch can save between 500,000 and 1 million gallons of water annually. That's the amount of water an average family uses over several years. Add to this savings on fertilizers and lawnmower work, and the benefit becomes obvious. Every year, the world produces over 500 million tons of glass. Without it, there'd be no windows, smartphones, cars, or skyscrapers. But few people know that the journey to this perfect transparency doesn't start with glass at all. It starts with hot sand, heated in furnaces to temperatures exceeding 1,600 degrees Celsius. This isn't just manufacturing, it's modern-day alchemy. Millions of tons of sand transformed into an ocean of molten glass, floating on liquid tin to create a perfectly smooth surface. You're about to discover the secrets of this process right here. Before hot sand becomes a transparent window, it all begins in a quarry. The primary raw material for float glass is high-quality silica sand. It must be almost perfectly pure, with a silicon dioxide content exceeding 99.5%. This sand is extracted from special deposits, typically deep underground. One of the most prized is Ottawa sand from Illinois. Pale white, fine as flour, and exceptionally pure. Quarries operate like giant anthills. Excavators tear through layers of earth, whilst lorries, 40-tonners, haul the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones and the slightest impurities. Besides sand, glass contains several other components. Soda ash lowers the melting temperature. It's transported from salt deposits, particularly from Wyoming, in 23-kilogram bags or in bulk. Limestone stabilizes the structure. It's supplied from quarries and ground to a dust with particles under 1 millimeter in diameter. The mix also includes dolomite, aluminum oxide, saltpeter, and glass waste, what's called cullet. Cullet reduces the energy consumption for melting by up to 25%. After initial cleaning, all components are mixed in precise proportions, which are kept as trade secrets. A giant mixer the size of a two-story house prepares the glass flour mixture. The finished mixture is transported to production by lorry and sometimes by rail or even on barges. Storage temperature must be controlled, no moisture whatsoever. The warehouse resembles a sterile grain elevator with silos, each with a capacity of roughly 560 cubic meters. The mixture is then automatically fed into the glass furnace, where within just minutes, everything that was sand and dust yesterday transforms into a boiling ocean of glass. The mixture enters the heart of production, the glass furnace. It's a genuine industrial volcano, over 60 meters long, with temperatures reaching 1,600 degrees Celsius at the melting core. Raw materials are fed in automatically, several tons per hour. In the first 9 to 12 meters of the furnace, melting occurs. Components melt and merge into a glowing, viscous mass. Next comes the homogenization zone. The mass is stirred and matures until all bubbles and lumps disappear. And only then does it gently flow onto metal. This is where the magic begins. In the second stage, the mass enters a bath of molten tin heated to 1,100 degrees. The glass literally floats on the metal, spreading into an even ribbon. Thanks to surface tension and the perfect flatness of the tin, a mirror-smooth surface forms on both sides, without polishing, without presses. Thickness is controlled by stretching, special rollers, or electromagnetic fields either stretch or compress the glass ribbon. This way, the output can be glass ranging from 1.5 to 19 millimeters thick. The tin bath spans over 45 meters, and the glass slowly floats along it at speeds up to 7.5 meters per minute, cooling en route to 540 degrees Celsius. This is an absolutely critical moment, but even at this stage, it's not ready yet. Next comes the annealing zone. The glass ribbon passes through a long tunnel where it cools by several degrees per minute to relieve all internal stresses. Without this, the glass could later crack on its own. Its surface is like ice, smooth without a single scratch. The sheet size is impressive, up to 3 meters wide and over 9 meters long. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, searching for micro cracks, inclusions, stress points. Any find means that sheet's rejected. Cutting isn't mechanical anymore. Now it's laser or roller scoring. A microblade, similar to diamond, scores a line, and then gentle pressure snaps the glass precisely along that path. Sometimes sheets are cut straight to order, say 60 by 90 centimeters for construction glass or screen size for Tesla. Others go in standard formats to warehouses, where they're stored vertically on racks with rubber spacers. After cutting comes the calibration stage. Sheets are checked for thickness, geometry, straight edges. High-definition cameras scan every centimeter. Lasers analyze the corners. There are almost no human hands here, only at the final stage when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency, marking is its name, passport, and craftsman's signature all in one. It's in the marking zone that each piece of glass is given its identity, where, when, by whom, and for what purpose it was created. The most common method is laser engraving. A special laser burns microscopic dots onto the surface, creating an indelible frosted inscription. Font thickness is less than 2.5 millimeters. This inscription can't be removed without damaging the glass, which is precisely why it's often used as an anti-tamper code. Sandblasting is used for decorative or premium glass. Through a stencil, abrasive is applied to the glass under pressure, forming a raised frosted mark. Then there's marking with ceramic inks. This method is used at the stage before tempering. Special paint is applied by printing, then baked at temperatures exceeding 1100 degrees. This marking is colored, noticeable, and extremely durable. It won't wash off, won't wear away, and won't fade. Marking can be either technical or branded. For instance, windows in luxury homes often proudly display the manufacturer's logo. In some projects, marking is even used for authenticity verification. For example, glass for armored vehicles or government buildings receives a serial number and QR code. The final stage is documentation. Every sheet gets a record in the system, like in a hospital. What sort of patient it is, when it was born, what properties it has, and where it's heading. This matters because glass isn't always dispatched immediately. Some batches are stored for months until their time comes.
Every year, enough glass fiber rebar is produced worldwide to challenge the dominance of steel itself. This isn't science fiction, it's modern manufacturing. The world spends billions fighting rust, repairing bridges and car parks destroyed by corrosion. But there is a solution. A composite material that is twice as strong as steel, 4 times lighter, and simply does not know the meaning of the word rust. The market for this material is growing at 12% a year, and today you will see how hundreds of bobbins and a barrel of resin give birth to the building material of the future.
It all begins at one end of a vast workshop, in front of a structure that looks like a giant library for thread. It's called a creel. On a wall several meters high, hundreds, sometimes thousands of huge bobbins are mounted in neat rows. Wound onto each one is a fine glass thread or roving. This isn't the glass from your windows. It's a special glass fiber produced by melting glass and drawing it through microscopic holes. The result is a thread thinner than a human hair, but with incredible tensile strength. This will be the skeleton. From each of these hundreds of bobbins, a single separate thread is drawn, and they all converge into one thick, fluffy bundle.
This river of glass fiber now begins its journey. It passes through a system of guides and tensioners. Each of the thousands of threads must be held at exactly the same tension. If one thread sags while another is too tight, the load in the final product will be distributed unevenly, compromising its strength. The dry glass bundle is then slowly submerged in a bath filled with a thick, sticky, honey-like liquid. This is the polymer resin, the flesh that will be built upon the glass skeleton. It's a complex chemical cocktail. The base is typically a polyester, vinyl ester, or epoxy resin. To this, a hardener is added, a catalyst that will trigger a chemical reaction, turning the liquid into a solid plastic.
Various additives can also be mixed in. Pigments for color, UV inhibitors to protect the rebar from sunlight, and fire retardants. The purpose of this bath is to impregnate every single tiny fiber. The bundle must be completely saturated in the resin, leaving no dry spots. Now heavy and soaked in sticky resin, the bundle emerges from the bath and heads towards the point of its creation, the forming die. This is the heart of the entire process. Imagine a thick steel plate with the perfectly round, polished hole, its diameter precisely matching that of the future rebar. The die is heated to a specific temperature.
As the wet bundle is pulled into this hole, several things happen at once. First, the die acts like a press, squeezing out all excess resin. Second, it compacts all the glass fibers tightly together, forming a perfectly round rod. Third, the heat from the die initiates the first stage of the curing reaction. Emerging from the die, we can already see the familiar shape of a rebar, but it is still soft and vulnerable. So how does it get its famous ribbed surface? Immediately after the die, while the rod is still hot and pliable, a special glass fiber strand is wound around it. A thin resin-soaked thread is wrapped in a spiral around the surface of the rod, creating the textured pattern.
The formed and wrapped rod now enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber which can stretch for dozens of meters, where a high temperature, typically around 200 degrees Celsius, is maintained. Here, the final transformation occurs. This isn't just drying. Under the heat, the resin molecules begin to rapidly link together, forming a strong, rigid, three-dimensional grid. The liquid, sticky syrup turns into an exceptionally strong and hard composite material, permanently bonding millions of glass fibers into a single, monolithic rod. As the rebar moves slowly through this hot tunnel, it acquires its final, rock-hard strength.
But what is pulling it through this long journey? At the end of the line sits a special pulling device. It typically consists of two caterpillar-tracked mechanisms like those on a tank, positioned one above the other. They gently but very firmly grip the finished solid rebar and pull it towards them at a constant, precisely controlled speed. It is this machine that provides the force to draw the glass fibers through the resin bath, the forming die, and the oven. The speed of this movement is one of the most critical parameters controlling the quality of the final product. And so, from the other end of this long production line, an endless, perfectly straight, hard and hot GFRP rod emerges. The final act is cutting. An automatic saw is mounted across the line. It synchronizes with the speed of the moving rebar, and at the right moment, it makes a quick forward dash, and with a sharp whiz, it cuts a standard length, for example 6 or 12 meters, from the continuous rod. It then returns to its starting position. The finished, still warm rebars roll onto a cooling table, after which they are collected into bundles, tied, and sent to the warehouse. And so, before our very eyes, thousands of fragile glass threads and a barrel of sticky liquid have journeyed through baths, presses, and ovens to become the lightweight yet incredibly strong building material of the future.
The market for glass fiber rebar isn't yet a giant like the steel market, but it is the boldest newcomer, rapidly gaining traction. The global market for this material is already valued in the hundreds of millions of dollars, with staggering forecasts. It's expected to grow by 10 to 12% annually. Now for the key features that are making the steel industry nervous. The first and most obvious is weight. GFRP rebar is roughly 4 times lighter than steel of the same diameter. Imagine a lorry
It can deliver 4 times more GFRP rebar in a single trip than it could steel.
On the construction site, 2 workers can easily carry entire coils of GFRP rods, whereas moving steel requires a crane. This represents a colossal saving in logistics and labor. Second is strength. And here, GFRP steps into the ring and knocks steel out in the first round. Its tensile strength is approximately twice that of standard steel rebar. This means that for some structures, a smaller diameter rebar can be used, saving even more on weight and volume.
But the ultimate advantage, the true superpower of GFRP, is its war on rust. The main enemy of any reinforced concrete structure, from bridges to car parks, is not the load, it's rust. Water and salts penetrate through microcracks in the concrete, reach the steel rebar, and it begins to corrode. Rust expands in volume and literally bursts the concrete from within. And GFRP? It simply laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means the lifespan of the structure increases dramatically. A concrete structure reinforced with steel is designed for about 50 years. A structure with GFRP rebar can easily be designed for a lifespan of over 100 years. Every year, more than 50,000 tons of uranium are mined across the globe. But to extract just a few grams of its energy, mountains of rock must be moved. It's a journey that begins in a desert where the temperature hits 38 degrees Celsius and ends inside a reactor that powers New York City. It involves centrifuges that spin faster than a jet turbine and chemicals that can dissolve metal in seconds. But the most interesting part is something that even the safety manuals don't mention. Watch until the end and you will learn a secret that will change how you think about nuclear power forever. It all begins in the dust, literally. Uranium ore is mined in hot, arid regions: Arizona, Wyoming, Texas, New Mexico. Here, the sun is relentless, reaching 38 degrees Celsius in the shade, if you can find any. There are 2 main extraction methods: open pit mining, where the topsoil is stripped away, and underground mining, with explosives and hoists. There is also a third, more subtle technique: in situ leaching. Pipes are drilled deep into the earth. Special solutions are pumped down to dissolve the uranium directly from the rock, and the resulting liquid is then pumped back to the surface. The ore itself, a grayish-brown rock, looks unremarkable, but within it, the crucial isotope uranium-235 makes up just 0.7%. The rest is a vast, almost useless mass that is inert in a reactor. And to squeeze the required drop of energy from it, hundreds of tons must be processed. After mining, the ore is crushed, milled into a fine powder, and thrown into a chemical bath of acid or alkaline solutions. This is followed by filtration, precipitation, and drying at 260 degrees. The final product is yellow cake, a bright yellow uranium concentrate. Officially, it's known as uranium ore concentrate, but everyone at the plant just calls it yellow cake. It looks striking, a mustard-colored loose powder like a spice for a barbecue. But this is a substance you must not touch and must never inhale. It emits alpha radiation, has a long half-life, and its dust is dangerously toxic. The yellow cake is sealed in double-walled drums, loaded onto escorted trailers, and plastered with radiation warning signs for the journey to the enrichment facility. This is the start of the path that turns a poisonous dust into the clean white light from a lamp over your kitchen table, or the electricity that powers the tube deep beneath London. Right, the yellow cake has arrived. It's radioactive, dry, and sealed in its drum. The next step? Turn it into a gas. And not just any gas. This is uranium hexafluoride. The uranium concentrate is first dissolved in acid, purified, and converted into uranium dioxide. And here, the alchemy begins. The uranium dioxide is treated with fluorine gas in special reactors at 540 degrees. The reaction creates a volatile, transparent gas that boils at just 56 degrees. A little heat, and it turns from solid crystals into a vapor. But it's not that simple. This gas is extraordinarily toxic. It corrodes most metals, destroys human tissue, and on contact with humid air, it instantly transforms into hydrofluoric acid and uranyl fluoride, a lethal cocktail. That is why this entire process is conducted inside sealed, automated reactors. The substance is stored as solid, whitish crystals, formed by cooling it to room temperature. These crystals are kept in steel cylinders, each engraved with a serial number and a radioactive symbol. A single cylinder weighs almost 14 tons. You think your washing machine spins fast? You haven't seen a nuclear centrifuge. They can reach 70,000 revolutions per minute, more than 10 times faster than a jet engine turbine. And all for one purpose, to separate uranium isotopes. Uranium hexafluoride, that toxic gas we just created, is fed into a tall, narrow cylindrical chamber, which is then spun at an insane speed. Centrifugal force does the work. The heavier uranium-238 atoms are flung towards the outer wall, while the lighter, crucial uranium-235 atoms remain closer to the center. But one centrifuge isn't enough. They are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas and passes it to the next. This process is repeated, cycle after cycle, until the concentration of uranium-235 reaches at least 3 to 5%. This is the standard grade for reactor fuel. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it is converted back into a solid, this time a ceramic form. After a series of chemical reactions, the gas becomes uranium dioxide powder, a dark gray solid. This powder is pressed under 20 tons of pressure into small cylindrical pellets, just 8 millimeters in diameter. They look almost harmless. Next, the pellets are centered in a furnace at nearly 1,650 degrees, making them as hard as porcelain. They are then polished and ground to precise dimensions. The finished pellets are loaded into long metal tubes known as fuel rods, typically made of a zirconium alloy because it resists corrosion and can withstand intense radiation. Each rod holds over 300 pellets. The rods are hermetically sealed and then bundled together into modules called fuel assemblies. They look like a square frame holding a grid of several dozen rods. A single assembly can weigh over 680 kilograms and will operate inside a reactor for up to 6 years. The finished fuel is packed into armored containers for transport. The journey is made under guard, on a special route with a security escort and GPS tracking. Left over from all of this is the depleted uranium hexafluoride, known as tails. It's a mix of isotopes with a small amount of U-235 remaining, but not enough to be useful. These tails are stored in steel cylinders at designated secure sites. When a fuel assembly has served its 4 to 6 years in the heart of the reactor, it is no longer a shining star. It is removed by a robotic system and moved into a deep pool of water, over 6 meters deep. The water cools the assembly and shields the intense radiation because the fuel is still incredibly hot. It rests there for several years. After that, it has 2 possible futures: long-term dry storage in concrete and steel casks, or reprocessing. This usually happens in other countries, as the US and UK primarily store their waste rather than reprocess it. In a dry storage facility, the assemblies stand for decades, cooled by natural air convection, as if in a nuclear monastery. This isn't the end, but a new phase of life. A slow, controlled existence, but one deeply connected to the future of energy. Because even after its time in a reactor, this fuel remains a source of heat, a lesson in engineering, and a reason for profound respect.
What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would grind to a halt, lights would go dark, and rocket engines would fall silent. And here's the thing. It's so rare that the entire world is competing for every single gram. Tungsten has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. That's a temperature at which most other metals would have long since turned to vapor. Annual global tungsten production ranges from 85 to 100,000 tons per year. But here's what's striking. Up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, showing just how valuable it is. Total global tungsten reserves are estimated at roughly 3 to 3.5 million tons, nowhere near the reserves of iron or aluminum. But here's what really matters. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that will flip your understanding of the metal holding civilization together. Picture a massive underground mine somewhere in Vietnam, China, Russia, or Canada, the world's biggest tungsten producers. Deep in the Earth's belly, hundreds of feet down, lie ores containing tungsten. Not pure metal, but complex minerals, wolframite and scheelite. Wolframite is a compound of iron, manganese, and tungsten. Scheelite is calcium tungstate. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep underground. It's tough, dangerous work, requiring high-tech equipment and strict safety standards. Thousands of tons of ore get hauled to the surface daily by massive underground trucks. Powerful blasts shatter the rock, exposing the valuable ore. It's like a controlled earthquake in miniature. After the blast, the ore gets loaded into haul trucks with capacities up to 300 tons and transported to the processing plant. After extraction, the ore goes to a processing plant. Here it undergoes several stages to separate valuable wolframite or scheelite from other rocks. First, the ore is crushed in crushers and mills into a fine powder. Massive jaw crushers with deafening roars break down car-sized chunks into fist-sized pieces. Then the crushed ore enters ball mills. giant rotating drums filled with steel balls. In these mills, the ore is ground into an extremely fine powder, almost like flour. Next, various enrichment methods are applied, such as gravity separation, magnetic separation, and flotation. Gravity separation uses the difference in density. Tungsten minerals are heavier than waste rock. Magnetic separation separates weakly magnetic wolframite particles from non-magnetic impurities. Flotation is a process where the ground or powder is mixed with water and special chemical reagents in large tanks. These reagents selectively attach to tungsten mineral particles, making them water repellent. Air is then pumped through the mixture, creating millions of tiny bubbles. The tungsten mineral particles latch onto these bubbles and rise to the surface, forming a foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The resulting concentrate is then processed at metallurgical plants to obtain pure tungsten. This is a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent calcination to produce tungsten oxide. The concentrate is dissolved in alkaline solutions at high temperatures. Ammonium paratungstate, an intermediate compound, is then precipitated from the solution. This compound is calcined at temperatures around 1100 to 1500 degrees Fahrenheit, producing tungsten oxide, a yellow powder. Tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. Inside specialized furnaces, tungsten oxide is heated in a stream of hydrogen. The hydrogen strips away oxygen from the tungsten oxide, releasing pure metallic tungsten. The result is a fine gray tungsten powder, the foundation for every product that follows. It's from this powder that tungsten rods, bars, and other blanks are formed through sintering. The tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, forming a dense, durable material. Sintering temperatures can reach 5400 degrees Fahrenheit. At that temperature, the powder particles begin to fuse, creating a monolithic structure. The process takes place in furnaces with controlled atmospheres to prevent oxidation. One of the most critical applications is the production of hard alloys known as tungsten carbides. These alloys, combining tungsten with carbon, plus cobalt or nickel as a binding agent, rank among the hardest man-made materials. Tungsten carbide is created by heating tungsten powder with carbon at temperatures around 2500 to 2900 degrees Fahrenheit. Tungsten carbide crystals form, which are then ground into powder. This powder is mixed with cobalt or nickel, serving as a binder, pressed into molds, and sintered. Tungsten carbides are used to manufacture cutting tools, drill bits, milling cutters, lathe tools that can machine the hardest metals and alloys. Without tungsten carbides, modern mechanical engineering, metalworking, and oil and gas extraction would be impossible. 2 pounds of tungsten can become a drill bit capable of boring thousands of feet through rock, demonstrating its incredible efficiency. Tungsten is also widely used in the military industry for manufacturing armor-piercing shells and bullet cores. Thanks to its high density and hardness, tungsten alloys have excellent penetration characteristics, providing high effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is irreplaceable. It's used to produce filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components requiring high heat resistance and electrical conductivity. Because of its high melting point, it's used in the space industry for components subjected to extreme temperatures. High-temperature alloys containing tungsten are used in aircraft engines, turbines, and other devices operating under conditions of extreme heat. Alloying with tungsten increases the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with lower toxicity. Plus, tungsten is used to create ballasts and counterweights in race cars, aircraft, and yachts thanks to its high density. It's also a component in certain jewelry pieces because of its hardness and scratch resistance. Tungsten is one of the least abundant elements in Earth's crust, which makes its mining and production especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential but not yet explored resources, the total volume could be significantly higher. This is, of course, incomparably less than reserves of metals like iron or aluminum, which underscores its strategic value. Annual global tungsten production, measured in tons of pure metal or tungsten oxide equivalent, fluctuates, but in recent years it's been approximately 85 to 100,000 metric tons per year. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine being able to take a worn-out tool that's already served its purpose and turn it back into something new, without spending energy and resources mining ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is among the most advanced and efficient of all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, demonstrating its value and economic viability. Where does used tungsten come from? The main source of secondary tungsten material is, of course, spent cemented carbides. Those cutting tools, drill bits, and milling cutters made from tungsten carbide. After intensive use, they wear down, lose their edge, or break. Instead of tossing them in a landfill, they're collected and sent to recycling plants. Other sources include tungsten-containing scrap metal, leftovers from tungsten product manufacturing, plus certain electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of ore mining and initial processing. Recycling dramatically reduces tungsten production's environmental footprint. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production greener and more responsible. And so, after a journey from underground blast through grinding into powder, and through flotation with millions of bubbles, through chemical dissolution and reduction in a hydrogen atmosphere at 1800 degrees, through sintering at 3000 degrees, a metal is born with the highest melting point on Earth, capable of withstanding 6192 degrees Fahrenheit, a metal without which modern industry, aviation, aerospace, and medicine would be impossible. And the most remarkable part, nearly half of this metal is born anew from old tools, making tungsten one of the most environmentally friendly strategic materials of our civilization. What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged. Heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy. The process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit, depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses, machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry, and remarkably, the core principle hasn't changed since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers, entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.
Every year in Dubai alone, over 1 million tons of asphalt are produced, and that number is constantly rising. Imagine it, tankers carrying millions of barrels of crude oil dock at Jebel Ali port. The oil is distilled in reactors at over 350 degrees Celsius, and a black, heavy residue is transformed into an advanced, elastic bitumen. Then come minerals from the mountains of Fujairah, processed at hundreds of tons per hour, blended in automated mixers, and transported in insulated trucks. This is the engineering magic that gives Dubai roads that neither melt in the sun nor crack in the night. Watch until the end, and you will discover the secret that makes this asphalt tougher than the desert itself. It all begins on the waters of the Persian Gulf, where giant tankers slowly cut through the surface, carrying millions of barrels of black gold, crude oil. They journey from Iraq, Saudi Arabia, and Kuwait. When a tanker docks at a port in the UAE, such as Jebel Ali, a process begins where men and machines work as a single organism. The oil is pumped into vast storage tanks, hidden within the industrial landscape, marking the start of its transformation. From there, it travels underground through a network of pipelines, like arteries leading to the heart of the refineries. In Jebel Ali or Abu Dhabi, it is met by a city of steel, reactors, distillation towers, and chrome columns. Here, the crude oil is heated to over 350 degrees Celsius to separate it into fractions. Lighter components, petrol, diesel, kerosene, vaporize first. The heaviest residues, the ones that refuse to vaporize even at these temperatures, are exactly what we need. This residue is fed into a vacuum distillation column, where the pressure is dropped to a minimum. What remains is bitumen, a black, viscous substance, the soul of asphalt. On its own, however, this bitumen is too thick and brittle for road construction, especially in a desert where the surface temperature can reach almost 50 degrees. So it must be modified. In special reactors, the bitumen is blended with polymer additives, plasticizers, stabilizers, and sometimes even crumb rubber. This is the bitumen modification process. The result is a material with high elasticity and resistance to UV radiation, one that won't soften under the sun or crack when the temperature plummets at night. In Dubai, a polymer-modified bitumen that meets the strict standards of the RTA, the Emirates Roads Agency, is used almost exclusively. Once the bitumen has completed its transformation, it begins the next stage of its journey, delivery to the asphalt mixing plants. The modified bitumen is transferred from the reactor into insulated storage tanks which maintain its temperature at around 175 degrees. In this liquid state, it remains perfectly uniform. It is then pumped through high-pressure sealed pipelines to the nearby plant or loaded into road tankers with special thermal containers. These tankers are built with a double-skinned steel body and a thick insulating layer. The drivers undergo special training. They must maintain a steady speed and monitor temperature sensors in real time. If the temperature begins to drop, an onboard heating system activates. At the plant, for example, the DXB asphalt factory in Dubai Industrial City, the tanker connects to the intake system. At this moment, the bitumen is hot, thick, and has a distinctive smell. It is pumped into the plant's holding tanks, where it waits to be precisely dosed. From this point on, it is no longer just a material. It is a component in a formula, where the weight, viscosity, and temperature of every ingredient will determine the lifespan of the road it is destined to become. One of the largest plants is the DXB asphalt factory. Here, the bitumen is heated to 160 degrees and mixed with mineral aggregates, gabbro, basalt, and quartz sand. Gabbro is a dark volcanic rock quarried in the mountains of Fujairah. The rock is crushed into fractions smaller than 25 millimeters, screened through vibrating sieves, dried in huge rotating drums, and then fed into the mixer. Inside, the bitumen and aggregates are combined into a hot, uniform mass known as hot mix asphalt. The temperature of the mix is 160 degrees. It must be perfectly homogeneous, with a precise ratio of components. After mixing, the asphalt is transferred to insulated silos where it can be stored for no more than 6 hours. From there, it is loaded into insulated trucks for the final journey. On site, the asphalt is laid by paving machines and then compacted by rollers, first vibratory, then static. In the desert, achieving maximum density is critical to prevent the ingress of sand and water. Compaction is done in multiple passes, and the temperature of the asphalt must not drop below 120 degrees Celsius during the process. If it does, the mix loses its workability and the road's integrity is compromised. A key feature of Dubai's highways is their multi-layered structure. The base course is made of a coarse-grain asphalt. The middle, or binder course, uses the modified bitumen and acts as a shock absorber. The top, or wearing course, is a thin layer with a high polymer content to provide grip and durability. In some cases, reflective minerals are added to reduce heat absorption. In the desert, it's not just the heat. Dust, wind, and humidity changes all have an impact. Asphalt plants in Dubai are equipped with advanced air filtration systems, and the mixes themselves are tested for resistance to abrasive wear and thermal expansion. In the RTA's laboratories, every batch of asphalt is checked for viscosity, density, and thermal stability. If it fails to meet the standards, the entire batch is rejected. This journey, from oil tanker to finished highway, takes several days, but involves dozens of quality control stages. And it is because of this meticulous process that Dubai's roads can withstand the daily punishment from thousands of vehicles without melting under the desert sun. Over 1 million tons of asphalt are produced in Dubai annually, and this figure is growing with the city's infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, allowing it to supply major projects without interruption. For comparison, an average plant in Europe produces around 150 tons per hour. Interestingly, asphalt is the most recycled material in the USA, with over 99% of old pavement being reused. Dubai is also actively adopting recycling, especially during the reconstruction of older highways. Somewhere in the world right now, a concrete giant is being born, capable of spanning a space as wide as an entire basketball court, And all of this without a single support. How can a lightweight hollow slab withstand the weight of hundreds of tons? Why do builders say that within these slabs lies the power of steel muscles? And most importantly, what secret makes them so unique that annually in North America, over 17.5 million square meters of these structures are produced, the area of 30 pentagons? Stay until the end, and you'll discover the secret that will forever change your understanding of concrete. The slip former machine crawls along a 590-foot forming bed at approximately 4 feet per minute. Doesn't sound terribly fast? Now let's do the maths. That's 200 feet per hour. That's nearly the length of an Olympic swimming pool, born from concrete in less than an hour. During a single 10-hour shift, one such bed can churn out almost half a mile of perfectly formed concrete slab. Now for the main feature, the voids. These holes inside aren't simply for aesthetics. They reduce the slab's weight by nearly 50% compared to a solid slab of the same thickness. Imagine constructing an office center with a floor area of 100,000 square feet. If the floors were made from ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just removed 2,000 tons of excess weight from the building. That's the weight of roughly 500 adult elephants, which foundations and columns no longer need to support. This allows the entire building structure to be made lighter, more elegant, and most importantly, considerably cheaper. But how can such a lightweight slab be strong? The secret lies in those tension steel muscles. The concrete used in these slabs isn't what you have on your pavement. This is high-strength concrete, withstanding pressure exceeding 8,000 pounds per square inch, whilst ordinary concrete manages only 3,000 or 4,000. And the steel cables inside are tensioned with such force that they create constant compression within the slab. That's precisely why these slabs are adored for constructing car parks, supermarkets, and open-plan offices. Annually in North America, over 17.5 million square meters of hollow core floor slabs are produced. This figure simply doesn't fit in one's head. It's an area sufficient to construct 30 buildings as gigantic as the Pentagon. Every year. This isn't merely a building material, it's an entire industry built on speed, efficiency, and intelligent use of resources. Everything begins not in a concrete mixer, but on a gigantic, perfectly flat aerodrome inside the workshop. This is the forming bed. Imagine a perfectly level, polished steel runway several feet wide, but in length 400, 500, and sometimes 600 feet. Beneath this runway lie pipes through which hot water or steam circulates to keep it warm. At both ends of this runway stand massive steel anchors embedded in thick concrete foundations. Between these two anchors, high-strength steel cables or strands are tensioned. This isn't ordinary wire. It's several steel threads woven together, each capable of supporting the weight of a motor car. They're laid along the entire length of the 590-foot bed, forming the future skeleton of the slab. One end of each cable is securely fixed in the anchor. To the other end is connected a gigantic hydraulic jack, and this jack begins to pull. It tensions each of these steel cables with a force of 30 or 40,000 pounds. The steel muscles tense up, becoming as hard as the strings of a gigantic guitar and store colossal energy within themselves. This is secret number 1, pre-stressing. When the steel skeleton is tensioned, the main character enters the stage, the forming machine or slip former. This is one of the most astonishing machines in the construction world. Imagine a strange, squat, self-propelled creature that slowly crawls along rails beside our long bed. At the top, it has a large hopper into which concrete is poured. But this isn't ordinary liquid concrete. This is so-called zero-slump concrete. It's so dry that it resembles damp earth. And so this machine begins its slow journey. Secondly, special vibrators and compactors with incredible force tamp this dry mixture, making it extraordinarily dense. And thirdly, most importantly, inside the machine are special forming tubes that, whilst vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth voids. The machine, like a gigantic concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab. Because the concrete is so dry, it instantly holds its shape and doesn't spread. This is secret number 2, voids that make the slab 50% lighter than a solid one. When the machine reaches the end of the 590-foot bed, its work is complete. But our slab is still green and weak. The time arrives for a spa treatment. Workers cover the entire length of this concrete ribbon with enormous insulating tarpaulins. Hot steam is fed beneath these tarpaulins. This creates a sauna effect that dramatically accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength. But in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened, the moment of release arrives. Workers slowly release the tension on the hydraulic jacks. Now it's not simply concrete, it's pre-stressed or compressed. This means that when a load acts upon it from above, attempting to bend it, it must first overcome this built-in compression force. This is precisely what allows it to span enormous distances without additional supports. And the final act of this performance? Cutting. Along rails beside our long concrete ribbon travels a gigantic saw. This is a monster with an enormous disc covered in industrial diamonds. With a deafening roar and fountain of sparks and water, this saw cuts the slab with incredible precision into pieces of the required length. Ready, perfectly level, lightweight, and incredibly strong slabs are lifted by gigantic cranes and loaded onto lorries.
Every hour across the globe, dozens of nuclear reactions. But only a handful know that at the heart of every atomic bomb lies a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, crafted by human hands. You'll discover how ordinary uranium births an explosion with the force of 1,000 suns, why sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret hides inside a nuclear warhead. Watch until the end, because the finale will change how you see the modern world. Back in the day, when the world was just learning to hear the voice of the atom, a few curious minds peered inside the invisible, into the heart of matter. Those were the years when science was feeling its way forward, but with great determination. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered that uranium could split. It was as if ice cracked on a river, behind which a giant lay sleeping. While Europe prepared for war, a group of people secretly gathered across the ocean, later to be called the Masters of Atomic Fire. In the New Mexico desert, the Manhattan Project began. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, beneath the clouds of dawn, the first nuclear bomb exploded. Sand turned to glass, sky to fire. And in the absolute silence, one scientist whispered, "Now I am become death, the destroyer of worlds."
But the story didn't end there. Days later, Hiroshima and Nagasaki became pages of grief. And just when the world thought it had seen everything, the USSR answered. Under Igor Kurchatov's leadership in 1949, the first Soviet atomic bomb detonated. A decade later, the Tsar Bomba. Its power could level a city the size of Paris. History's irony. Nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. Ideas of security, control, diplomacy became more important than warfare. For the first time, humanity faced massive questions. Can we negotiate so everyone survives? That's how deterrence doctrine was born. Don't attack, because you know attacking means catastrophe. And while this balance is far from perfect, it's delivered decades without global war between superpowers. An entire era. Cold, anxious, but without mass battlefronts.
Nuclear research sparked whole new industries: nuclear power, reactors on submarines, medical diagnostics. Even space projects got a boost from understanding the atom. To create the most terrifying thing, we learned to grasp the most complex. Yes, nuclear weapons are dangerous, but they're also a mirror of human wisdom. We built something incredibly powerful and chose not to use it on a massive scale. This is a story about power we decided to restrain, about science that taught us not to dominate, but to coexist. Deep in laboratories, where lamplight dimly illuminates blueprints, the path to building a nuclear bomb begins. This isn't just assembling metal, it's modern-day alchemy, where every gram of material holds the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction.
But natural uranium is mostly uranium-238, which won't work, so they enrich it, separating out the 235 isotope using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It's produced in nuclear reactors, where uranium absorbs neutrons and transforms into plutonium, the stuff you need for a nuclear bomb. The appearance of a nuclear bomb often resembles a classic aircraft bomb, a streamlined metal casing engineered for stable descent from high altitude. In a massive hangar where the walls ring with the echo of metal, the air smells of hot steel and oil. Here begins the birth of the shell that must contain the heart of an atomic explosion. From the glowing throat of an industrial furnace flows a stream of metal, special steel, reinforced with nickel, chromium, and manganese. Its temperature exceeds 1,000 degrees. Summer sunlight looks pale compared to this fire.
Masters in protective suits with transparent face shields watch the forming process.
Steel sheets bend into streamlined shapes under presses exerting hundreds of tons of force. Before their eyes, an elongated body takes shape, resembling a water droplet frozen under the pressure of the heavens. Next, mechanical arms mill the internal partitions, cut openings for tail stabilizers and locking mechanisms. Every fraction of an inch, the result of meticulous calculation, because balance during descent depends on it. After this, the casing undergoes a strengthening ritual: immersion in an anti-corrosion bath, treatment with polymer coating, application of matte paint. The color? Dark green, like a military shadow in the twilight of pine trees. And finally, testing. They drop it from height, strike it with hammers, spin it in a wind tunnel. Only after passing all trials is the casing ready to receive its lethal payload.
A quiet lab, half light, a faint smell of ozone, something heavy hangs in the air. In front of you lies an open nuclear bomb, its metal casing removed, its insides, like an organism, laid bare. There's nothing extra here, no shine, no decoration, just function, just explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear core. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in your palm. Its shape, mathematical perfection, polished down to microns. Around the sphere, an entire symphony of pressure. Composite explosives, layer upon layer, like a flower turned inside out. Their job isn't simply to detonate, but to force the explosion inward. Like hands clenching to the limit, these explosive lenses must create implosion, uniform, merciless compression that drives the material supercritical.
If even 1 second lags, the whole contraption becomes a heap of meaningless metal. And at the very heart of this implosion orchestra, the initiator, a tiny device waiting for its moment to release the first neutrons. Polonium and beryllium interact, creating a minuscule storm capable of triggering the irreversible. That's where the chain reaction begins, a match to an atomic forest. Then, the tamper layer. Heavy as a shadow, it wraps the bomb's core not for protection, but for containment. Uranium-238 or tungsten, not active, but absolutely critical. Their job? Delay the neutrons, force them back like an echo in a cave. Everything depends on this. The duration of the blast, its power, its climax. In the tail section, the brain. Automation, electronics, wires and sensors. Barometers waiting for altitude, radars tracking the ground, batteries sleeping, ready to wake.
This is where it's all decided, when everything happens, above the city, in the air, after the drop. Without this nervous system, the blast would be an accident. But here, it's a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, like chapters in an encyclopedia of force. The outer shell, smooth and cold. The explosive layer, mathematically arranged. The tamper, an invisible guardian. The core, like a seed of what's to come. And at the very center, a spark, sleeping until awakened. Over 62 years, the world witnessed 2,065 nuclear explosions. 5,224, that's not the number of nuclear explosions, but an approximate estimate of the entire U.S. arsenal, including active, reserve, and decommissioned warheads. Now, the number of nuclear tests that the United States conducted from 1945 to 1992 totals 1,154 detonations.
Each one is a separate page in the history of power, fear, and science. The first blast, Trinity, July 16, 1945, in the New Mexico desert. It was the beginning of an era when atomic energy became a weapon. Then came Hiroshima and Nagasaki, the only instances of nuclear weapons used in combat. In the decades that followed, the U.S. tested bombs at Enuatak and Bikini atolls, in Nevada, underground, in the atmosphere, over water. The blasts had different purposes: testing new designs, demonstrating power, studying effects on equipment and living organisms. Yield varied,
from a few kilotons to 15 megatons, like in the Castle Bravo test of 1954. In 1952, the US conducted its first thermonuclear test, Ivy Mike. This wasn't just a bomb anymore, but a miniature star created by humans. The explosion wiped out an entire island. In the 1960s, testing became routine. The US tested warheads for missiles, aerial bombs, even neutron charges that had minimal blast waves but maximum radiation. The last official detonation happened on September 23, 1992, after which the US declared a moratorium, but the arsenal remained. It gets modernized, adapted, stored. Some warheads are on submarines, some on strategic bombers, some in NATO storage facilities. These explosions aren't just technical events. This is a story about how humanity learned to control the energy of stars and put it in the service of fear. But it's also a reminder that the power capable of destroying civilization sits under the control of those who understand the price of using it. And as long as this balance holds, the world continues to exist on the edge of the abyss, but doesn't fall in.
Every year, the world mines thousands of tons of metals, but only one is so dangerous it can kill you even as dust, and yet helps us peer 13 billion years into the universe's past. That's beryllium, a metal lighter than aluminum but many times harder than steel, a metal without which the James Webb Space Telescope wouldn't exist. But there's one detail almost nobody talks about. Why does producing it feel like a chemical nightmare? And why does working with it become a deadly gamble? And what exactly are those factories hiding behind thick, protective glass? Subscribe so you don't miss out. You'll learn something that'll forever change how you think about metal. Let's jump straight to the numbers, because they're absolutely mind-blowing. Look at this block of metal. Appears to be just another gray hunk of iron, but try to lift it and you'll nearly clock yourself in the chin from the surprise. Beryllium has a density of just 1.85 grams per cubic centimeter. That's almost 30% less than aluminum, which we've always considered the gold standard for lightness. But here's the kicker. Despite being this lightweight, beryllium is 4 times stiffer than steel. Its elastic modulus hits an incredible 303 gigapascals. What that means is this material puts up insane resistance to any deformation. You could build a structure thin as paper, and it would still hold its shape under colossal stress. On top of that, beryllium has this exceptional ability to maintain its strength at high temperatures, making it absolutely irreplaceable in the aerospace industry. The extraction process, that's a whole chapter in the textbook of industrial survival. The primary source here is a mineral called bertrandite, mined in the deserts of Utah. The ore contains just 0.5% beryllium. To extract this metal, the rock gets crushed and dunked into sulfuric acid, turning everything into a chemical slurry. Then, through a series of complex manipulations with hydroxides and fluorides, they get pure beryllium fluoride. They mix it with magnesium in massive crucibles and heat it up to 2400 degrees Fahrenheit. The magnesium grabs the fluorine, and shiny metallic grains settle to the bottom, so-called pellets, or beryllium pebbles. Each grain is only a few millimeters across, but it's from these tiny pieces that parts for spacecraft and military hardware will eventually be assembled. But this is just the beginning, because working with them directly is impossible. And here's where we get to the most dangerous part of the tour. Beryllium is a genuine toxic bomb. Its dust causes chronic beryllium disease, which basically makes your lungs shut down. All it takes is breathing in a microscopic amount of particles and your immune system starts attacking your own tissues. The disease can show up years after exposure, when you've long forgotten that one day you spent at the facility. So nobody here pours the metal into molds like cast iron. Instead, they use powder metallurgy methods. Metal grains get ground into fine powder in special mills under vacuum. Every single dust particle has to be controlled. Then, they pour this powder into massive steel capsules and subject it to vacuum hot pressing. Imagine hundreds of atmospheres of pressure and temperatures over 1800 degrees Fahrenheit, simultaneously crushing this powder, forcing it to become a solid block. This goes on for hours until the structure becomes perfectly uniform. Why did the telescope engineers choose this hellish material for their mirrors? It's all about the cold of space. James Webb operates at Lagrange Point 2, about 930,000 miles from Earth, where temperatures plunge to minus 370 degrees Fahrenheit. Regular glass deforms unpredictably when it cools this much, expanding in one spot, contracting in another. But beryllium has a unique property. Its thermal expansion coefficient at low temperatures becomes virtually zero. It basically freezes in place. The shape stays constant no matter how brutal the cold gets. This made it possible to build mirrors that remain perfectly smooth even in the savage cold of deep space. Each of the 18 mirror segments measures 4.3 feet across but weighs just 44 pounds. If they were made from glass, each one would tip the scales at over 200 pounds. And the rocket simply couldn't lift off the ground. Each mirror was carved from a single block, removing 90% of the mass from the back to create a lightweight honeycomb structure. This is called lightweighting. The walls there are just a few millimeters thick. After that, polishing begins. It's done using computer systems that remove irregularities measured in nanometers. 1/1000th of a meter. That's the precision we're talking about here. If Webb's mirror were the size of the Atlantic Ocean, the biggest bump on its surface wouldn't be taller than a regular coin. Then the mirrors are taken to a cryogenic chamber, where they're cooled to space temperatures, microscopic warping is measured, and then they're polished again to compensate for those changes. This cycle was repeated dozens of times over several years. Now take a look at this color. We're used to seeing telescope mirrors in gold, but underneath that gold lies pure beryllium. The gold is only applied at the very end through vacuum deposition. The gold layer is just 100 nanometers thick. That's 1,000 times thinner than a human hair. The entire massive mirror, covering about 270 square feet, used only about 1.7 ounces of gold. That's like 3 or 4 wedding rings rolled out across a giant surface. Gold is essential because the telescope searches for infrared radiation from the very first stars that ignited 13.5 billion years ago. Beryllium provides rigidity and stability, while gold delivers perfect reflection in the precise wavelength range needed. At this facility, safety protocols look like paranoia, but it's justified paranoia. See those yellow lines on the floor? You can't cross them without special footwear. The air in the shop completely refreshes every 3 minutes. Beryllium levels in the air must not exceed 0.2 of a microgram per cubic meter. That's so small you couldn't even see it under a microscope. But sensors are everywhere. After every shift, each worker goes through a special shower, and their clothing gets disposed of as hazardous waste. That's the price we pay for the ability to peer into the depths of space. But beryllium isn't just about space. Look at these tiny components for aircraft engines. Because beryllium conducts heat better than most metals, it's perfect for parts that need to cool down fast. Its thermal conductivity is around 210 watts per meter Kelvin. It pulls heat away faster than aluminum and doesn't melt until 1287 degrees. This lets planes fly faster and engines run more efficiently. Here's another wild fact you probably won't hear in chemistry class. Beryllium is almost transparent to X-rays. Take an X-ray through a steel plate, you'll see nothing. But with beryllium, the rays pass through like it's not even there. That's exactly why the windows in every X-ray machine and CT scanner at hospitals are made from beryllium foil. It lets doctors get crystal clear images of your body without losing radiation power at the machine itself. So what does all this cost? If you want to buy a kilogram of pure beryllium, expect to shell out anywhere from $800 to $1,000. But that's just raw material. The cost of a finished part can be 10 times higher or more because of how difficult it is to machine and all the safety precautions required. A single web mirror segment costs millions of dollars when you factor in all the years of testing and polishing. And even with these insane prices, global beryllium production doesn't exceed a few hundred tons per year. That's how rare and difficult it is to work with. Thanks for watching. Hit that like button if you love real science as much as I do. See you at the next classified facility.
Every knife in your kitchen, every spoon in your drawer, every sink, every pot, every bolt in a skyscraper. All of it exists because of one gray-green rock lying hundreds of feet underground. Nickel ore. Without it, stainless steel wouldn't exist at all. Nickel is what transforms ordinary iron into metal that won't rust for decades. Add 8% nickel to steel, and it withstands seawater, acids, extreme temperatures. Every year, humanity mines 3 million tons of this metal. Value: $50 billion. But the journey from rock in the ground to shiny stainless steel sheet? It's technological hell. Explosions in quarries. Smelting at 2,700 degrees Fahrenheit. Chemical baths with sulfuric acid. Electrolysis under thousands of volts. How do you get metal that's 99.9% pure from gray rock that looks like an ordinary stone? Watch till the end. You'll see how the foundation of modern civilization is born. Planet Earth holds 300 million tons of nickel, but it's buried deep. The biggest deposits are in Indonesia, the Philippines, Russia, Canada, Australia, China, and the US. Not miners, processors and consumers. America uses it for aerospace and nuclear reactors, but it all starts in the pits. Open pit mines in Indonesia are wounds in the jungle the size of a city. A pit 1,000 feet deep, 3 miles wide. Excavators with 700 cubic foot buckets gnaw at the earth around the clock. The ore here is called laterite. It's a reddish-brown rock that looks like clay. Just 1 to 2% nickel. The rest? Iron, silicon, magnesium. But even these scraps of nickel make mining profitable. One Belazi haul truck carries 300 tons of ore out of the pit. 500 trips like that a day. 150,000 tons of rock daily. That's an entire mountain of material you need to squeeze metal from. The ore heads to primary processing. Here it's crushed and sorted. Massive jaw crushers grind car-sized chunks down to 4-inch pieces. The noise is so intense workers wear noise-canceling headphones. Then cone crushers pulverize the rock to gravel size. Mills with hardened steel balls turn the gravel into powder. Inside a 65-foot rotating drum, 4-inch steel balls hammer the ore. After 6 hours of spinning, the rock becomes dust. This dust gets mixed with water. You get a liquid slurry, it runs through magnetic separators. Nickel ore is weakly magnetic, but the iron in it magnetizes stronger. Some of the waste rock gets filtered out. Nickel concentration in the slurry jumps from 2 to 4%. Still not much, but better. The slurry thickens in huge settling tanks. Water drains away, leaving wet paste. It dries in drum dryers at 400 degrees. What comes out is dry concentrate, ready for smelting. From 1,000 tons of ore, you get 300 tons of concentrate. (1751). Swedish chemist Axel Kronstedt is studying a strange mineral from the Lost Mine. The rock's reddish, looks like copper ore. Kronstedt tries to smelt copper from it, but gets a white metal unlike anything known. Hard, heavy, doesn't rust. He names it nickel, after Nickel the mountain spirit from German folklore, who tricked miners by slipping them worthless rocks instead of copper. But nickel turned out to be anything but worthless. In the 19th century, they start adding it to steel. The British discover that 5% nickel makes battleship armor twice as strong. The Germans use nickel steel for artillery. World War I turns nickel into a strategic resource. Whoever controls nickel controls military production. In the 30s, metallurgist Harry Brearley invents stainless steel. The formula is simple: 18% chromium, 8% nickel, the rest iron. This steel never rusts. Revolution in kitchens, hospitals, factories. Demand for nickel explodes. The hunt for new deposits begins worldwide. The 1960s. Discovery of massive deposits in New Caledonia and Indonesia. Laterite ores containing billions of tons of nickel. But there's a problem. These ores can't be smelted the conventional way. Too many impurities, composition's too complex. New technology is needed. The Canadians invent the Sherritt-Gordon process. The Chinese develop a pyrometallurgical method called RKEF. Rotary kiln, electric furnace, ferrochrome. Every country creates its own nickel extraction methods. By the 2000s, China becomes the dominant processor. They build dozens of plants in Indonesia and the Philippines. Strategy's simple: control the processing, control the market. The US took a different path. Americans focus on high-purity nickel for EV batteries and reactors. Smaller volumes, but the highest quality. A plant in Ontario processes Canadian ore using flash smelting technology. Temperatures above 2,900 degrees Fahrenheit. Metal purity, 99.999%. This nickel goes into Teslas and nuclear submarines. Two approaches, two philosophies. China wins through volume, America through quality. The smelting shop is the hottest place in the plant. In the center of the hall stands an electric furnace as tall as a 5-story building. Power output, 100 megawatts. That's like 10,000 homes running simultaneously. Nickel ore concentrate is loaded from the top along with coke and fluxes. Coke is pure carbon, the heat source. Fluxes, limestone and quartz, they bind the waste rock. Through graphite electrodes, they run a current of 100,000 amps. Voltage, 200 volts. Temperature inside the furnace climbs to 1,500 degrees in an hour. The ore melts. Heavy metals, nickel, iron, cobalt, settle to the bottom. Light slag floats to the top. This separation is critical. After 8 hours of smelting, the furnace is ready for tapping. A tap hole opens at the bottom. Molten metal flows through a channel into a ladle. It glows white-hot. Temperature 1,400 degrees. Workers in silver suits control the process remotely. One ladle holds 50 tons of metal. This is matte, an alloy of nickel, iron, and sulfur. Nickel content, 20%. That's not enough. Further refining is needed. They pour the mat into a converter, a massive horizontal barrel 50 feet long. Oxygen gets added too. The blow begins. Oxygen at 150 psi blasts into the molten mix through tuyères. The reaction's exothermic, releases so much heat the temperature shoots up to 3,000 degrees without any external heating. Sulfur and iron oxidize, burn off. New slag forms, gets drained away. After 6 hours of blowing, what's left in the converter is fine matte, an alloy with 50% nickel. But even that's not pure enough for high-tech applications. Next stage, electrolysis. The fine matte gets ground into powder and dissolved in sulfuric acid at 180 degrees. You get a green solution of nickel sulfate. This solution goes into electrolytic cells. Each cell, a tank 10 feet by 7, 3 feet deep. Inside hang titanium anodes and nickel cathodes. Between them, the solution. They run a current at 2 volts, current strength, 20,000 amps per cell. Nickel from the solution plates onto the cathodes. Over a week, each cathode builds up a layer of pure nickel about an inch thick. They pull the cathodes out, scrape off the nickel. Purity, 99.95%. And just like that, after passing through explosions, crushing, smelting at temperatures above 2,700 degrees Fahrenheit, oxidation, dissolving in acids and electrolysis, a dull gray rock transforms into a shining metal that changed the world. Without nickel, there'd be no skyscrapers, their steel frames would rust away in years. No submarines, seawater would eat through their hulls. No nuclear reactors, their pipes couldn't handle the corrosive environment. Every component that needs to last decades in conditions where ordinary steel surrenders contains nickel. 3 million tons per year. 200 consumer nations. Thousands of factories, millions of jobs. Indonesia digs the ore, China smelts the metal, America turns it into superalloys for space. Europe stamps out stainless steel for hospitals. A closed loop that keeps civilization afloat. Nickel isn't just a metal. It's a guarantee of durability for everything we build. Proof that humans learn to take nature's dull rocks and turn them into eternity. Every time you wash your hands in a sink that gleams like new after 20 years of service, remember, that's nickel at work. The metal that conquered time and corrosion. Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of 2 glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s, when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred: improvements to laminated glass, and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between two glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection, special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements, thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment. This is Duisburg, Germany, and right in the middle of this city stands the ThyssenKrupp steel plant, the biggest steel complex in the European Union. 15 square miles, 26,000 workers, 10 million tons of steel a year. That's more than entire countries produce. Every third car in Europe runs on steel that was born here. Every other refrigerator, every rail, every tin can, here. Today we're walking through this plant from start to finish. From a chunk of iron ore to a gleaming sheet of steel that tomorrow becomes the hood of your car. It doesn't start in Duisburg, it starts thousands of miles away, in the mines of Brazil, Australia, and Canada. Iron ore isn't pure metal. It's rock where iron is mixed with sand, clay, and dozens of other minerals. Average iron content in the ore runs between 60 and 65%. The rest is waste rock that has to be removed. The ore gets crushed in massive cone crushers down to a size of about 1/4 inch to 3/4 of an inch. Then it heads to the sintering plant, the first processing stage right at the Duisburg facility. Here, fine ore dust is mixed with coke breeze and limestone. The mixture gets laid down in a layer on a moving belt pallet conveyor and ignited from above by gas burners. Combustion temperature hits 2,200 degrees Fahrenheit. During sintering, the ore particles fuse together, forming porous chunks. Sinter. This isn't dust or sand anymore. These are solid porous lumps 3/4 of an inch to 2 inches across, perfect for loading into a blast furnace. The porosity of the sinter is critical. Hot air needs to flow freely through it during smelting. Every hour, the sintering belt produces between 800 and 1,000 tons of finished sinter. While agglomeration is happening at the plant, coking runs in parallel. Coke isn't just coal, it's chemically processed coal that releases carbon monoxide when burned, essential for reducing iron from ore. Regular coal won't cut it, it burns too fast and leaves too much ash behind. ThyssenKrupp's coke batteries are rows of vertical chambers, 23 feet tall and about 20 inches wide. Each chamber gets loaded with 25 tons of coal and heated to 2,000 degrees Fahrenheit without any air. The process takes 18 hours. During that time, tars, ammonia, hydrogen sulfide, and benzene evaporate out of the coal. These gases get captured and processed. They become fuel or chemical feedstock themselves. What's left is pure coke, silvery black porous chunks, hard as rock. When the chamber door opens, a special ram pushes the glowing coke onto a quenching car. A column of fire and smoke shoots up 65 feet. The car races to the quenching tower, where thousands of gallons of water come crashing down on the red-hot coke. Steam and smoke engulf everything around. Within minutes, the coke cools to 200 degrees and it's ready for the blast furnace. The blast furnace is the heart of the entire plant. ThyssenKrupp in Duisburg has 4 of them. Each one is a cylindrical steel tower standing 260 feet tall, lined on the inside with refractory brick. From the top, they continuously load the charge, layers of sinter, coke, and limestone in precisely calculated proportions. From below, through tuyères, openings about 3 inches in diameter, superheated air at 2,200 degrees Fahrenheit blasts in at nearly 60 pounds per square inch. When that scorching air hits the coke, it ignites at temperatures exceeding 3,600 degrees. Oxygen from the air reacts with the carbon in the coke and forms carbon monoxide. This gas rises up through the charge and reduces the iron oxides, strips the oxygen right off them. The iron is reduced and, in liquid form, trickles down to the bottom of the furnace. Slag flows down there too, a liquid mass of molten limestone and rock. Every 4 to 6 hours, they tap the pig iron through a tap hole, a special opening in the lower part of the furnace. First, they drill through a plug of refractory clay with a pneumatic drill, and from the opening, streams of liquid metal at 2,700 degrees come gushing out with a hiss and a shower of sparks. One tap yields between 200 and 300 tons of liquid pig iron. Every day, each blast furnace produces between 4,000 and 5,000 tons of pig iron. Molten iron pours into massive ladles, cylindrical vessels with refractory lining that hold 300 tons. The ladle heads to the desulfurization station. Iron from the blast furnace contains up to 0.6% sulfur, a disaster for future steel quality. Sulfur makes metal brittle. It cracks during rolling and welding. Through a submerged lance, they blow in magnesium powder, or a mix of lime and calcium carbide. Magnesium reacts with sulfur, forming magnesium sulfide, solid slag that floats to the surface. A scraper removes the slag from the top. In 20 minutes, sulfur content drops from 0.6 to 0.02%. That's 30 times less. Now the iron's ready to become steel. They pour it into a basic oxygen furnace, a massive pear-shaped vessel holding 300 tons. From above, an oxygen lance descends onto the molten iron. From it, a jet of pure oxygen blasts out at several times the speed of sound. Ignition is instant. Temperature in the reaction zone exceeds 2,000 degrees. Carbon oxidizes, forming carbon dioxide. It bursts from the furnace with a column of flame and sparks. The whole process in the converter takes 20 to 25 minutes. During this time, the carbon content drops from 4% in pig iron to 0.2 in steel. At the same time, phosphorus, manganese, and sulfur residues are removed from the converter. The slag is poured off by tilting the converter. Then it's tilted the other way, and through the tap hole, the finished liquid steel is poured into a ladle. But that's not the end. The liquid steel goes to a secondary metallurgy unit. Here, alloying elements are added: chromium, nickel, molybdenum, vanadium, depending on what grade of steel is needed. For automotive sheet, one recipe. For pipeline steel, another. For packaging material, a third. ThyssenKrupp produces over 900 grades of steel. In a vacuum unit, dissolved gases, hydrogen and nitrogen, are removed from the steel. Hydrogen is especially dangerous. It diffuses into the metal's crystal lattice and can cause internal cracks hours after rolling. After vacuum degassing, hydrogen content drops below 0.02 cubic centimeters per 100 grams, a safe level for any application. The finished liquid steel heads to the continuous casting machine. This is the longest unit in the plant, almost 650 feet from start to finish. The liquid steel gets poured into a mold, a water-cooled copper form that sets the shape of the future blank. Coming out of the mold, the metal already has a solid shell about an inch thick, but inside it's still liquid. Gradually cooling on rollers, the continuous metal ribbon fully solidifies. Then it's cut with gas torches into slabs, 26 to 40 feet long, up to 6.5 feet wide, and 6 to 10 inches thick. One slab weighs 15 to 30 tons. ThyssenKrupp's continuous casting machine has a capacity of 500 tons per hour. The new fourth line, launched in July 2025 after 800 million euros in investment, significantly improved casting precision and metal purity. Hot slabs weighing 20 to 30 tons travel by roller table to the hot rolling mill. But first, the reheating furnace, a walking beam furnace 650 feet long. The slabs move slowly through it for 2 hours until the temperature equalizes throughout the entire cross-section to 2,300 degrees Fahrenheit. Uneven heating is catastrophic. If the center is even 125 degrees cooler than the surface, internal tears will form during rolling. After the furnace, the slab passes under the descaler. Water jets at 2,200 pounds per square inch blast away the scale, a layer of oxidized metal. scale 1/10 of an inch thick, if not removed, gets rolled into the surface and leaves defects. Then roughing begins. A reversing stand with rolls 4 feet in diameter presses on the slab with a force of 80,000 tons. In 7 to 9 passes back and forth, a slab 8 inches thick transforms into a transfer bar 3/4 to 1 1/4 inches thick. Length increases tenfold in the process. From a 26-foot slab emerges a 260-foot strip, racing at 10 feet per second. Absurd. Finish rolling is 7 stands positioned one after another, 50 feet apart. The strip passes through all 7 without stopping. In the first stand, thickness is about 3/4 of an inch. In the last, from around 1/20 to 3/4 of an inch, depending on the order. Speed builds from stand to stand. If the strip enters the first stand moving at around 3 feet per second, by the time it exits the 7th, it's already hitting 65 feet per second. That's 45 miles per hour. The strip flies like a silver ribbon. Tension is maintained between each pair of stands. If it drops, the strip runs off the mill and triggers an emergency shutdown. After finish rolling, the hot-rolled strip feeds onto a coiler, where it's wound into a coil weighing up to 30 tons and measuring up to 6.5 feet in diameter. Before coiling, the strip is cooled on a roller table with a water spray. Temperature drops from 1650 down to 930 to 1100 degrees. This coiling temperature is critical. It determines the metal's structure and therefore its mechanical properties. Each coil is automatically measured, weighed, and marked. The hot rolling mill at the Duisburg plant produces over 5 million tons of hot-rolled steel per year. Some of the coils go straight to customers. Construction companies, pipe manufacturers, shipbuilders. But a significant portion goes further, to cold rolling. Cold rolling is needed where a thin sheet of perfect quality is required. Automotive, appliances, food packaging. First, the coil is unwound and run through a pickling line. The hot-rolled strip is covered with an oxide film, scale. It's hard, abrasive, and interferes with further processing. The strip is pulled through baths of hydrochloric acid solution at 176 degrees Fahrenheit. The acid dissolves the scale but doesn't affect the metal itself. Then the strip is rinsed with water, neutralized with soda solution, and dried. Clean, shiny surface. Now it's ready to roll. A cold rolling mill is 4 or 5 stands in a line. Unlike hot rolling, where the metal is pliable from heat, here it's rolled cold. Roll pressure. Up to 100,000 tons per meter of strip width. The sound in the shop? Continuous metallic thunder. Vibration felt through the soles of your boots. From a thickness of 2 to 4 millimeters, the strip is stretched to 0.6 to 1 millimeter. That's a reduction of 4 to 6 times. Rolling speed at the exit on up to 30 meters per second, 67 miles per hour. Cold rolling strengthens metal but makes it brittle. This is called work hardening. The crystal lattice deforms and stops the movement of dislocations, and dislocations are what give you plasticity. To restore flexibility to the metal, you anneal it. At ThyssenKrupp, they use bell-type furnaces. Coils are stacked vertically on stands in groups of 3 to 4, covered with an inner bell and an outer hood. A protective gas, a mix of nitrogen and hydrogen, gets fed inside to prevent surface oxidation. The furnace slowly heats the coils to about 1,300 to 1,400 degrees Fahrenheit. At this temperature, the metal atoms get enough energy to restructure the crystal lattice. Deformed grains get replaced by new ones, smaller and more regular. This process takes 18 to 24 hours. After heating, the furnace cools slowly, another 24 to 36 hours. You can't rush it. Uneven cooling creates residual stresses and warping of the sheet. After annealing, the metal's soft and pliable again. But the surface has gone dull. The rollers left behind micro-roughness. For automotive bodies, that's unacceptable. The final rolling stage is skin pass rolling. It's a light pass with a reduction of just 0.5 to 2%. The goal isn't to reduce thickness, but to give the surface the right roughness and finally flatten the sheet. Skin pass rolls have a special surface that transfers onto the strip. Automotive sheet needs minimal roughness. It has to stamp well and be perfectly smooth under the paint job. Roofing steel needs more roughness so paint grips better. After skin passing, the strip gets cut or left in a coil, depending on the order. But most of the sheet goes further, to the coating lines. The most common coating is galvanizing. The continuous hot dip galvanizing line. The strip unwinds, gets cleaned in an alkaline solution, passes through an annealing furnace, then plunges into a bath of molten zinc at 840 degrees Fahrenheit. A zinc coating forms on the surface, 0.3 to 1/1000th of an inch thick on each side. Air knives, jets of compressed air, blow off excess zinc and even out the coating thickness. This coating protects the steel from corrosion for 20 to 30 years. It's this galvanized steel from Duisburg that covers the bodies of most cars in Europe. Finished rolls of galvanized steel head to the warehouse and out to customers. Each roll comes with a quality certificate, 20 to 30 pages long. It lists the chemical composition down to thousandths of a percent, mechanical properties, yield strength, tensile strength, elongation, hardness. It documents the temperature and duration of every single production stage. If a problem pops up a year later at a customer's plant, engineers can trace the entire production history of that specific roll down to the minute. Every year, the Duisburg plant processes 40 million tons of raw materials and produces 10 million tons of finished steel. 234 years in one spot, and the plant still beats at the very heart of European industry. If you found it fascinating to see how steel is born, from iron ore to the perfect sheet for your car, hit that like button on this video. Drop a comment if you knew that 1 ton of steel hides an entire factory of chemical reactions inside it. And subscribe to the channel. Here we open up the industries that quietly hold our world together.
Every year, the world produces over 500 billion glass bottles. If you line them up in a single row, they'd wrap around the Earth more than 3,000 times. These are mountains of gleaming, fragile material that could remain in landfills forever, forming glass deserts for thousands of years. But a portion of this material gets a second, third, 100th chance at life. How exactly does an ordinary lemonade bottle, tossed into a recycling bin, pass through fire and mechanical hell to become crystal clear and ready for use again? Behind this lies a colossal technological process that rivals space programs in precision and scale. If you watch to the end, you'll discover the main secret of why glass is called the immortal material, capable of infinite reincarnation without losing quality. And it's precisely this property that makes it a genuine marvel of engineering and ecology. The journey to glass rebirth doesn't start at a factory. It starts on our city streets. Recycling begins with collection. In advanced countries like Germany or Switzerland, this is a well-oiled system where every citizen plays a part. Special containers for clear, green, and brown glass stand on every corner. Moreover, in many European countries, there's a fund system, a deposit included in the beverage price. By returning an empty bottle to a special machine at the supermarket, you receive a voucher that can be used towards purchases. This transforms rubbish collection from a duty into a profitable venture. In other regions, there's an entire shadow army of collectors, people for whom returned bottles are their main source of income. The collected glass flows along logistical arteries, from small trolleys to massive refuse lorries towards recycling plants. It's here, on these noisy and dusty sites, that the first act of its resurrection begins. After tons of glass bottles arrive at the plant, they face their first test, sorting. And this is where technology worthy of science fiction enters the game. Along a wide conveyor belt rushes a motley stream. Clear bottles from water, green ones from wine, brown ones from beer. The human eye can't keep pace with this speed. So optical scanners based on near-infrared technology are installed above the conveyor. A light beam penetrates through the glass while sensors analyze how it refracts. Artificial intelligence determines the chemical composition and color of each fragment in fractions of a second. Color sorting is critically important. Just one green bottle can contaminate an entire ton of raw material for clear glass, giving it an unwanted tint. After identification, the system issues a command. Powerful jets of compressed air shoot with surgical precision at the right fragments, knocking them off the conveyor into separate compartments. But color is only half the battle. Along with glass, the stream contains numerous foreign objects: metal caps, plastic rings, paper labels. Here begins multi-level cleaning. First, the conveyor passes under giant electromagnets. With a deafening clang, they snatch all steel caps from the stream. Then, eddy current separators come into play. They create a magnetic field that repels non-ferrous metals, like aluminum, forcing them to literally jump off the belt into a separate container. After this, powerful fans blow away light rubbish, paper and plastic. And finally, the glass passes through a water cleaning system where organic residue and dirt are washed away. Just imagine the complex journey every bottle we discard takes before becoming clean raw material. After sorting and cleaning, the glass is sent to its execution, the crusher. This is an enormous machine whose steel jaws or hammers grind entire bottles into small fragments with a deafening roar. The sound is as if thousands of chandeliers are simultaneously shattering. Several types of crushers exist: jaw crushers that crush glass between two plates, and hammer crushers where hammers spinning at furious speeds smash glass against a steel wall. This stage's goal is to transform bulky and fragile bottles into a uniform mass called cullet. This material is far more convenient for transport and, most importantly, for melting. At this stage, any remaining impurities not removed earlier can be additionally screened out. After crushing, the cullet is sieved through a system of vibrating screens that calibrate it by size. Even after crushing, cullet may contain microscopic metal or organic particles invisible to the eye, so it undergoes final, even more thorough cleaning. Magnetic separation here works at a new level, capturing the tiniest metal inclusions. Then special optical technologies are used to remove ceramic or porcelain remnants, which look like glass but have different melting temperatures and can cause defects in the finished product. This guarantees that absolutely clean material enters the furnace. Then the glass crumb is sent to vibrating sieves, where it passes through several levels of screens with different mesh sizes for separation into fractions. Different grain sizes are used for different types of products. This entire process is fully automated, minimizing risks for workers. After all stages of cleaning and calibration, the purest cullet is sent to the factory's heart, the melting furnace. At the plant, it's loaded into gigantic furnaces where it melts at temperatures from 1530 to 1650 degrees Celsius. At such heat, glass becomes liquid, viscous, and fiery red, like lava. Adding cullet to the melting process is not just ecological genius, but economic genius too. Recycled glass melts at a lower temperature than primary raw materials, sand, soda ash, limestone, which reduces energy consumption by 30%. Sometimes a small amount of new raw material is added to the melt to adjust the chemical composition and guarantee the strength and transparency of future products. After the glass transforms into a uniform liquid mass, its rebirth begins. The molten lava is directed into forming machines. Here, a drop of molten glass under air pressure transforms into a new bottle, jar, or vase in seconds. At large plants, this process is fully automated and can include high-precision molds to ensure perfect quality. Immediately after forming, the red-hot glass products pass through a long annealing tunnel, where their temperature gradually and very slowly decreases. This is a critically important stage that relieves internal stresses in the glass and prevents cracking. After forming and cooling, new glass products undergo ruthless quality control. Special robotic systems check every bottle for the slightest defects, air bubbles, micro cracks, uneven wall thickness, or incorrect shape. Optical scanners and lasers illuminate the glass, revealing flaws invisible to the eye. If a product doesn't meet the highest standards, it's ruthlessly rejected and sent back for remelting. Then, bottles are tested for mechanical strength, checking whether they can withstand the pressure of carbonated drinks and impacts during transport. Only after passing all these tests are new glass products packaged and dispatched to market. Thus completes one cycle of their endless life. Every year, millions of tons of wood waste are generated worldwide, and most of it could simply vanish into landfills. But this is where a remarkable story begins, transforming ordinary wood chips, shavings, and even old furniture into solid boards that become the foundation of our everyday comfort. This isn't just manufacturing, it's a second life for timber. Picture mountains of raw material as tall as a 5-story building disappearing into steel monster machines only to emerge in a completely new form. And right now, we're about to reveal all the secrets of this process, which combines scale, precision, and a touch of engineering wizardry. It all starts at a massive raw material yard, where the foundation for future boards arrives in a continuous stream. Contrary to popular belief, high-quality timber is almost never used in their production. On the contrary, the manufacturing philosophy is all about giving wood waste a second life. Mountains of raw material are brought here, reaching heights of dozens of meters. The foundation is industrial wood chips obtained from low-grade timber. A huge proportion comes from sawmill waste, slab wood, offcuts, and thin battens. Wood processing waste is also heavily used, such as shavings and sawdust generated at furniture factories. A separate and important category is reclaimed timber. Old wooden pallets, crates, and even used furniture are given a chance at a new life as part of chipboard after thorough cleaning. Every batch of raw material undergoes strict incoming quality control. The first stage of cleaning is removing metal inclusions. Powerful electromagnetic separators screen the flow of raw material, extracting nails, staples, and any other metal fragments. The material then passes through screening systems to remove sand, stones, and other debris. If whole logs are used in production, say 20-foot lengths, they must pass through a debarking machine. Inside a massive rotating drum or using special cutters, the bark is stripped away. This step is critically important because bark has a different structure, contains loads of dirt, and significantly deteriorates bonding quality. The prepared and cleaned timber begins its journey along a conveyor belt hundreds of meters long, carrying it towards the first stage of mechanical transformation. It disappears into the steel jaws of a giant chipping machine, an industrial monster the size of a small room. Spinning at thousands of revolutions per minute, its blades bite into the timber with incredible ease, transforming solid pieces into a stream of uniform chips a few centimeters in size. But this material is only semi-finished. The resulting chips are too large and coarse. So the next step is finer, more precise secondary grinding, which takes place in specialized particle mills. It's here, amid the roar of high-precision equipment, that the actual wood particles are born, the ones that give the final product its name. At this stage, the geometry of the particles becomes absolutely crucial. For the outer, face layers of the board, which will be responsible for its appearance, very fine, thin, and flat particles are needed. These are produced in knife ring fakers, which literally slice thin flakes off the chips, resembling cornflakes. For the inner, core layer of the board, which forms its structural backbone, larger and thicker particles are used. This creates a strong internal framework that gives the board its final rigidity, bending strength, and the ability to reliably hold fixings such as screws and bolts. The resulting moisture mass has varying moisture content, which is unacceptable for quality bonding. So all the particles are sent to one of the most crucial stages, drying. Typically, huge drum dryers are used for this. Particles flow continuously into a rotating drum where they're blasted with hot air. The final moisture content of the particles must be within a very narrow range, from 2 to 6%. If the particles are over-dried, they won't absorb the adhesive properly. If they remain too moist during hot pressing, excess steam can literally blow apart the board from within. Now comes the turn of the key component that will transform the loose mass of particles into a monolithic board, the binding agent. Most commonly, these are synthetic resins. The sorted particles enter special continuous action mixers. Inside them, resin is sprayed through nozzles, creating an adhesive mist that evenly coats every wood particle. Resin dosage is critically important and typically ranges from 6 to 10% of the dry particle mass. The resin-coated particles, now sticky and ready for bonding, are finally prepared to become board. They're transported to a massive forming machine where scattered particles give birth to a continuous particle mat. This is where the engineering magic of creating a 3-layer structure happens. The forming machine is a complex system that sequentially and with high precision deposits particles onto a moving conveyor belt. First, it creates a perfectly even bottom layer using the finest fraction. Immediately after this, a significantly thicker middle layer is laid onto this foundation, consisting of large and strong particles. Finally, the entire mat is covered with another layer of fine fraction, creating a mirror image of the bottom layer. This precisely calibrated structure, resembling a sandwich, provides unique properties to the future board. Its smooth and dense outer layers are ideal for subsequent sanding, whilst the strong internal layer gives the board its necessary rigidity. The formed but still loose mat passes through a prepress, where it's significantly compacted. This prepressing removes excess air and gives it a shape convenient for loading into the main press. This is the culmination of the entire technological process. The pre-pressed and cut mat sections are fed into the hot press. Inside the press, two powerful forces act simultaneously on the particle mass. Enormous pressure, reaching dozens of kilograms per square centimeter, compresses the particles. At the same time, the press plates, heated to 200 degrees Celsius, transfer their heat to the mat. This high temperature activates the resin, triggering an irreversible polymerization process. The liquid adhesive instantly transforms into an extremely hard and durable polymer, which permanently bonds millions of wood particles together. During this brief moment, the loose mat transforms into a hot, solid, and absolutely monolithic chipboard. Hot boards straight from the press can't be stacked immediately. They need to cool gradually to relieve internal thermal stresses. For this, they're placed in special star coolers, where they're ventilated for several hours. The next step is calibration and sanding. Boards pass through multi-head sanding machines, where wide abrasive belts remove a thin surface layer, bringing the board to its precise specified thickness and creating a perfectly smooth surface. At the final stage, large production boards are cut into standard commercial formats and their edges are trimmed. Finished products undergo strict quality control. Only quality boards are marked and sent to the warehouse. Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything, from selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are microcracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer, and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1/1000th of a gram. Excess or shortage means danger for the shooter and weapon. 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. But installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics. Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed, automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture.
Every year, over 150 million cubic meters of plywood are produced worldwide, enough to have a train of wagons loaded with these sheets circle the Earth at the equator several times. But how is an ordinary tree trunk turned into this unique material, used in furniture, construction, and even shipbuilding? What secrets does the process hide? Starting with spa treatments for logs and ending with a hot press where layers of wood are permanently bonded into a monolith. Watch until the end and you'll learn about the secret pencil that remains after production and why it too has its own value.
It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, or pine. After delivery to the factory, the logs undergo the first and very important stage of preparation, hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours and sometimes a whole day. This kind of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible. After the bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface.
The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk like a scroll of ancient papyrus, turning a 3-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer.
The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor while hot air intensely blows on them from all sides. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks.
At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table, and on top of it, a sheet coated with glue. And here lies the main secret. Each subsequent sheet is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, and the third's lengthwise again. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split and evenly distributes the load. That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-story structure, between whose plates several dozen future plywood sheets are loaded simultaneously. With an enormous force reaching tens of kilograms per square centimeter, the plates compress the veneer layups. At the same time, the plates are heated to a temperature of 150 degrees Celsius. Under the influence of high pressure and temperature, the glue polymerizes, permanently bonding the layers into a single, incredibly strong monolith.
Hot sheets of plywood come out from under the press and are stacked for gradual cooling. After this, they undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, or glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a marking is applied to it. The finished stacks of plywood are sent to the warehouse to later become part of furniture, houses, and ships.
The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets.
And now imagine what holds enormous suspension bridges in the air, which daily withstand the weight of thousands of cars and hurricane-force wind gusts. Not concrete and not steel in the columns, but an invisible hero, steel cable. From thin, almost fragile wires, they create structures capable of bearing hundreds of tons. The secret lies in technology that transforms a simple metal rod into a sinew that never gives in. American factories have already woven over 800,000 kilometers of cables, and each meter is like a separate artery of civilization. But there's a detail that's not written about in textbooks, and you'll discover it only at the end of this video. Everything begins with selecting raw materials, high-quality steel wire that must possess exceptional strength and flexibility. These wires pass through a cold drawing process where thick steel rods are pulled through special holes, gradually reducing their diameter to thin but extraordinarily strong threads. This process doesn't simply make the wire thinner, it enhances its mechanical properties, making it resistant to breaking. Imagine that each meter of this wire can withstand enormous loads whilst remaining flexible and elastic. After the wire is ready, the most interesting part begins, forming the steel cable. Dozens and sometimes hundreds of such threads are twisted into strands, then woven into complex structures. Each wire layer has its purpose. Internal threads bear the main load, whilst external ones protect against wear and corrosion. The entire process resembles creating living tissue, where each thread is a separate vein that together forms a strong and reliable whole. Particularly impressive is the precision and control with which these cables are manufactured. Each stage is accompanied by strict testing. They check tensile strength, resistance to bending, and impact of weather conditions. Testing is conducted using special equipment that simulates the loads the cable will experience during bridge operation. This is extremely important, as bridges often stand in human environments or in locations with aggressive climates. Thanks to these coatings, cables not only maintain their strength, but also extend the bridge's service life, ensuring safety and reliability. Imagine the production scale. Factories that can manufacture thousands of tons of steel cables annually, unwinding and weaving hundreds of kilometers of wire. American manufacturers, for example, have many years' experience and employ the most modern technologies, allowing them to create cables for the world's most famous bridges. It's known that American Bridge Company has laid over 800,000 kilometers of steel cables for suspension bridges. Another aspect that impressed me is the role of engineers and technologists who constantly improve production processes. They work to make cables even stronger, lighter, and more resistant to extreme loads. Using new alloys, improving twisting and coating methods, all this makes modern steel cables genuine masterpieces of engineering thought. During the tour, I saw how enormous spools of steel wire move smoothly along conveyors, how wire passes through cold drawing, and how craftsmen control every centimeter of this process. American manufacturers, such as American Bridge Company, have enormous experience in manufacturing steel cables for the country's largest and most famous bridges. They produce thousands of tons of cables annually using modern technologies and strict quality control. It's known that for suspension bridges, they use cables with multi-layered structure that can withstand loads of hundreds of tons per square centimeter. During Brooklyn Bridge construction, for example, each of the main cables consisted of 19 separate strands, and each strand of 278 wires. This provided an enormous strength reserve. Steel cable production in the U.S. is a combination of tradition and innovation, where the craftsmanship of engineers and technologists is complemented by automated lines and modern equipment. Each stage, from raw material selection to protective coating application, is controlled with maximum attention, as thousands of people's safety who daily use bridges depends on this. European enterprises, particularly in countries like Germany, France, Italy, as well as Ukraine, Romania, and Poland, play an important role in supplying steel cables for bridge construction of various scales. Modern bridges are the result of millennia of engineering thought development, where traditions, innovations, and the most modern materials combine. They not only perform the function of connecting shores, but also become city symbols, cultural monuments, and technical masterpieces. Modern engineering marvels include the Falkirk Wheel in Scotland, a unique rotating boat lift that connects two canals and allows lifting boats through 180 degrees. This structure is not only functional, but also impresses with its futuristic design. Cable-stayed bridges, such as the Golden Gate in San Francisco, demonstrate the application of steel cables that withstand enormous loads and ensure structure longevity.
Today we're going on an incredible journey. From massive crankshafts that power ocean vessels to precision railroad components that keep millions of passengers safe. Settle in and let's dive into the mesmerizing world of industrial manufacturing. Here we're witnessing something truly impressive, the machining of a massive marine crankshaft weighing over 15 tons. This isn't your typical workshop project. These crankshafts are the beating heart of container ships and cruise liners, converting the explosive power of diesel engines into rotational motion that propels these ocean giants across our seas. The star of the show, a revolutionary vertical boring mill. Rising nearly 3 stories tall, this engineering marvel features a 20-foot diameter faceplate capable of machining parts up to 65 feet long. The machine's spindle delivers an impressive 1,600 horsepower while maintaining accuracy tolerances of just 4/10,000ths of an inch. That's thinner than a human hair. An advanced computer numerical control system coordinates up to 12 simultaneous axes, ensuring every cut is executed with mathematical precision. Watch as the massive crankshaft rotates at a carefully controlled speed of 15 revolutions per minute. Carbide cutting tools, each costing more than a luxury car, slice through hardened steel like butter. The cooling system pumps 500 gallons per minute of specialized cutting fluid, preventing thermal distortion while washing away chips that look more like metal ribbons. Notice how the operator monitors vibration sensors and thermal cameras. At this scale, even tiny deviations can spell disaster. The real magic happens during the finishing passes. Using diamond-tipped tools, surface finish reaches an incredible 0.4 microns, smoother than a mirror. Laser measurement systems continuously verify dimensions, while ultrasonic testing ensures the internal structure remains intact. This single crankshaft will operate for decades, generating millions of horsepower cycles. It's a testament to German engineering precision that transforms raw steel into a mechanical masterpiece worth over $500,000. Welcome to where they've redefined what heavy duty really means. This isn't just another CNC lathe. This is a mechanical monster engineered to tackle the roughest, toughest machining jobs in heavy industry. When aerospace manufacturers need to machine titanium landing gear components, or when power plants require custom turbine shafts, this is where they turn. This beast can handle parts up to 5 feet in diameter and 40 feet long, weighing up to 25 tons. The main spindle generates 400 horsepower through a precision planetary gearbox, delivering massive torque at low speeds. Watch the machine attack this massive steel workpiece with aggressive roughing cuts. The cutting parameters are mind-blowing. Depth of cut just over ½ inch, feed rate around a 32nd of an inch per revolution, removing over 200 cubic inches of material per minute. High-pressure coolant jets at 1,000 pounds per square inch blast away continuous ribbons of steel chips that could fill a pickup bed in just minutes. Advanced vibration damping and thermal compensation systems maintain dimensional accuracy within 0.02 of an inch across the entire part length. The CNC system with adaptive control technology automatically adjusts cutting parameters based on real-time force and temperature feedback. It's like having a master machinist's intuition built right into the machine's brain. Step into the world of railroad wheel manufacturing, where safety and precision aren't just priorities, they're matters of life and death. Every single day, millions of passengers trust their lives to these wheels, which must withstand enormous forces, extreme temperatures, and millions of rotation cycles. From high-speed trains racing across the European countryside to heavy freight locomotives hauling cargo across the American plains, the wheels we're about to see represent the culmination of over 150 years of railroad engineering evolution. Our journey begins with carefully selected steel billets, heated to a blazing 2,190 degrees Fahrenheit in massive induction furnaces. Watch as the glowing steel is shaped by 8,000-ton forging presses that deliver forces equivalent to the weight of 800 elephants. This forging process aligns the steel's grain structure, creating the incredible strength needed to support rail cars weighing 25 tons. The wheels are then normalized in computer-controlled furnaces, cooling slowly over 48 hours to achieve the perfect balance of hardness and toughness. Quality control begins immediately. Ultrasonic testing reveals any internal defects that could prove catastrophic in service. Now the precision work begins. Each wheel blank is mounted on state-of-the-art CNC wheel lathes, masterpieces of German engineering capable of maintaining tolerances tighter than the thickness of paper. These machines feature massive chucks 10 feet in diameter that grip the wheel with hydraulic pressure equivalent to 50 car jacks. The cutting tools are specially designed carbide inserts, each costing $200 and engineered to maintain sharp edges through thousands of cuts. Computer vision systems scan each wheel, creating a three-dimensional map that guides the machining process. This is where artistry meets engineering. The wheel profile isn't just a simple curve, it's a complex mathematical shape that determines how the train will ride, steer, and brake. Watch as the lathe creates the tread surface with its precise 1-in-20 taper, the flange that keeps the train on the rails, and the intricate root radius that prevents stress concentrations. Each cut is monitored by laser sensors measuring to within 0.01 millimeters. Surface finish must be perfect. Any imperfections will create wear that could lead to derailment at 200 miles per hour. Here we're looking at one of the most demanding machining operations out there, boring and facing an 8-inch diameter hole through massive steel components. This isn't your typical drilling operation. We're talking about creating precision holes through materials that could stop a tank round. These operations are common in heavy industrial applications like hydraulic cylinders for mining equipment, deep hole drilling for oil drilling, and cylinder blocks for massive diesel engines. The horizontal boring mill dominates this operation with its massive spindle assembly, capable of reaching several feet into the workpiece. The boring bar itself, a precision tool weighing hundreds of pounds, must remain absolutely rigid while cutting forces try to deflect it. Advanced vibration damping systems and precision spindle bearings ensure cutting tool stability. The cutting insert, $300 of carbide engineering, must maintain a sharp edge while removing cubic inches of steel per minute. Watch as a massive cutting tool begins its journey through steel, creating this perfect 8-inch hole. The cutting parameters are carefully calculated. Too aggressive, and the boring bar will deflect. Too conservative, and productivity suffers. High-pressure coolant floods the cutting zone, not just for cooling, but to flush away the continuous stream of steel chips that could jam the operation. The machine's computer numerical control system automatically compensates for boring bar deflection, ensuring the final hole diameter stays within a tolerance of 0.01 inches across its entire length. Now comes facing, creating a perfectly flat surface perpendicular to the hole. The facing head, equipped with multiple cutting inserts, machines the surface at feed rates measured in thousandths of an inch. Once complete, this component could become part of a mining excavator's hydraulic cylinder, where it'll control movements of machinery weighing hundreds of tons. The precision we just witnessed ensures these systems run reliably for decades, moving mountains one bucket at a time. Our final segment showcases the artistry of complex turning operations, creating intricate threaded components that combine multiple diameters, sophisticated geometries, and precision threads in a single setup. These parts might look simple, but they represent the pinnacle of machining mastery, demanding perfect coordination of cutting tools, spindle speeds, and feed rates to achieve dimensional perfection across every feature. This component features multiple turned diameters, each with different tolerances and surface finish requirements. Notice the stepped geometry requiring different cutting tools for each operation, the internal threading that must align perfectly with external features, and the complex radii that seamlessly blend surfaces. The threading operation demands specialized thread cutting tools and precise spindle synchronization. The computer numerical control system coordinates spindle speed with carriage speed to create perfect thread pitch. Tool changes happen automatically, each cutting insert optimized for its specific operation. Single-point threading tools carve helical grooves with mathematical precision, creating threads that will mate perfectly with corresponding components. Thread pitch accuracy within 0.0001 inches, correct thread form angles, and perfect surface finish all combine to create threads exceeding commercial standards. The completed part undergoes comprehensive quality inspection using specialized thread gauges, optical comparators, and coordinate measuring machines. Every dimension, thread specification, and surface finish gets verified against engineering drawings. These complex turned parts often become critical components in aerospace applications, medical devices, or precision instruments, where failure isn't an option.
Every year, the world extracts over 8 million tons of gray, unremarkable ore. But only a tiny fraction of it undergoes an incredibly complex, almost alchemical journey to become a metal capable of withstanding even spaceflight. Titanium isn't just a metal, it's a substance born in hell from fire, chlorine, and magnesium at temperatures exceeding 1,000 degrees Celsius. Its first form looks like light ash, but from it they create the invisible skeleton of aircraft, eternal implants, and rocket engines. How does a chunk of dirty rock transform into a material stronger than steel yet lighter than aluminium? Watch to the end, and you'll see how an ordinary stone passes through chemical purgatory to become the heart of modern civilization. The history of titanium is the story of a ghost metal that remained hidden in plain sight for decades. In 1791, British clergyman and amateur geologist William Gregor, while studying black sand on the Cornish coast, discovered traces of an unknown element within it. But only 4 years later, in 1795, the great German chemist Martin Klaproth independently discovered the same element and named it titanium, after the mighty Titans from ancient Greek mythology. However, despite its thunderous name, the metal remained elusive. For nearly a century and a half, it slumbered in chemistry textbooks, resisting attempts to isolate it in pure form. Only in the 20th century, thanks to breakthroughs by American chemist Matthew Hunter and Dutch scientists, did humanity finally manage to touch pure titanium. From the mid-20th century, with the onset of the Cold War and the space race, titanium transformed from a laboratory curiosity into a strategic material. The United States, recognizing its colossal potential, invested enormous sums into its production. Titanium became the foundation for the legendary spy plane SR-71 Blackbird, capable of flying at the edge of space, and found its place in the construction of Apollo spacecraft. Titanium production begins with mining its ores, ilmenite and rutile. These minerals are found in the sands of Australia, Canada, and South Africa. After extraction, the ore undergoes multi-stage enrichment. It's washed, screened, separated from waste rock using magnets and gravity, yielding a dark, heavy concentrate. But this still isn't metal. This is merely titanium oxide, where it's firmly bound to oxygen. To break these molecular shackles, the concentrate is sent to chemical hell, into fluidized bed reactors. Here, at temperatures of 1,000 degrees Celsius, gaseous chlorine is blown into a boiling layer of ore and coal. A fierce chemical reaction begins. Chlorine tears titanium away from oxygen, forming a volatile compound, titanium tetrachloride. This caustic, toxic substance is then repeatedly distilled, purifying it from impurities to near-perfect purity. The next stage is the heart of the entire process, named after its creator, William Kroll. Into a sealed steel sarcophagus filled with inert argon gas, molten magnesium is placed. Then purified titanium tetrachloride is slowly fed in. A chemical duel begins. Magnesium, being a more reactive metal, literally rips chlorine atoms away from titanium. As a result of this battle, pure titanium settles at the reactor's bottom, but in the strangest and most unremarkable form imaginable. This is sponge titanium, a porous, lightweight gray mass that looks like frozen foam or pumice. It's brittle and utterly unlike strong metal. But inside this ugly porous sponge lies all the future might. This sponge is extracted, crushed, and then pressed under enormous pressure into dense briquettes. And only then is it sent to its final transformation, into the melting furnace. To transform sponge briquettes into a monolithic ingot, they're melted in vacuum arc furnaces. This is necessary because at high temperatures, titanium absorbs oxygen and nitrogen from the air with incredible greed, instantly making it brittle. Inside a sealed chamber, a powerful electric arc, like lightning, melts the briquettes, and liquid titanium flows into a copper, water-cooled mold. To achieve perfect uniformity, this process is repeated twice, sometimes even thrice. The result is a gleaming, silvery ingot of pure titanium, ready for further processing. Just look at this incredible transformation, from porous, lightweight sponge to dense, shining metal. But pure titanium is merely the beginning. To create materials for aviation and space, it's transformed into alloys. To molten titanium, like spices in a chef's dish, other metals are added. Aluminium for lightness, vanadium for strength, molybdenum for heat resistance. Thus is born, for example, the most famous titanium alloy, T6Al4V, which became the workhorse of the aerospace industry. These alloys are remelted several times to achieve perfect uniformity. The next stage is mechanical processing. Giant ingots are heated red hot to make them malleable and sent under presses or rolling mills. With incredible force, machines bend the metal to their will, transforming it into sheets, rods, beams, and wire. From these semi-finished products, the most complex parts are then cut, turned, and milled. But that's not all. In recent years, additive technologies, or three-dimensional printing, have entered the game. Special printers sinter the finest titanium powder layer by layer with lasers, growing parts of such complex geometry that traditional methods cannot achieve. This allows creation of lighter and stronger components for aircraft and rockets, saving up to 40% of weight. Every finished part undergoes the strictest control. It's X-rayed, scanned with ultrasound, checking for the slightest internal defects. In aviation, titanium has become indispensable. From it, they make up to 15% of a modern passenger airliner's weight, landing gear, wing elements, and of course, engine components. This significantly reduces the aircraft's overall mass and increases its fuel efficiency. In the medical field, roughly 70% of all implants, such as artificial hip joints or dental prosthetics, are made from titanium. Its unique biocompatibility means the human body doesn't reject it, allowing bone tissue to literally grow into the implant surface. This is a metal that becomes part of a person. Thus, having passed through fire and chemistry, an unremarkable stone transforms into high-tech material that pierces the heavens, explores space, and restores people's ability to move. But titanium conquered not only the sky, but also the darkest ocean depths. At the height of the Cold War, Soviet engineers created something unthinkable: submarines of Project Lyra, known to NATO as Alpha. Their hulls were made entirely from titanium. This allowed them to dive to depths unreachable by the enemy and develop underwater speeds exceeding those of torpedoes. These goldfish, as they were nicknamed for their incredible cost, became underwater phantoms, invulnerable to magnetic detectors and capable of escaping any pursuit. Titanium is the only material capable of withstanding the colossal pressure at depths of 800 meters whilst remaining sufficiently light. Moreover, its absolute resistance to corrosion in salt water makes it an eternal material for the marine element. So what's titanium's main secret, promised at the beginning? It's not just its strength or lightness. Its true magic lies in its ability to self-heal. Every time titanium's surface is scratched, it instantly reacts with oxygen from the air or water and covers itself with the thinnest, invisible, yet incredibly strong film of titanium oxide. This is a sort of invisible armor that instantly regenerates when damaged. It's precisely this film that makes it absolutely inert, preventing it from reacting with the human body or aggressive environments. But this superpower has another side, another secret. During mechanical processing, if proper technique isn't followed, fine titanium swarf can spontaneously ignite. This white fire burns at such high temperatures that it's impossible to extinguish with water or sand. Taming titanium is playing with fire in the literal sense. And only those who've mastered this art can make this mythical metal serve humanity.
What if I told you there's a metal that's 15 times rarer on Earth than gold? And to mine just 1 ounce of it, you need to process 10 tons of ore. A metal whose entire annual supply would fit in an ordinary room, while all the gold in the world would fill 3 Olympic-sized swimming pools? Every year, the world produces only 180 tons of platinum. That's 17 times less than gold. South Africa produces 120 tons, 74% of global production. Russia's in second place with 23 tons. To extract 1 ounce of platinum requires processing 10 tons of ore, while for gold, just 2 to 3 tons. The Merensky Reef, Upper Group 2, and Platreef contain only 2 to 10 grams of platinum per ton of ore. After flotation, the concentrate is heated to 1500 degrees Celsius to burn off iron and sulfur impurities. Then they use aqua regia, a mixture of nitric and hydrochloric acids, to dissolve the platinum. The concentration of platinum in Earth's crust is only 0.5 parts per million. Stick around till the end. You'll discover a secret that even jewelers won't tell you. Picture an underground mine several miles deep somewhere in South Africa, in the Bushveld province, home to the world's largest platinum deposits. These aren't open-pit mines. They're narrow tunnels blasted through rock up to 2 miles beneath the surface. Here, platinum is extracted from thin layers, reefs, that stretch for hundreds of miles but measure just 6 inches to 5 feet thick. 3 main reefs: the Merensky Reef, Upper Group 2, and Platreef. The Merensky Reef, discovered by Hans Merensky in 1924, has historically dominated global platinum production. Here, platinum reaches its highest concentration, 50 to 60% platinum group metals. Upper Group 2, a chromite-rich reef, more stable but with lower gold, copper, and nickel content. Platreef, a wider reef with lower platinum grades but higher base metal content, roughly 5 times more. Miners drill holes into the reef walls and pack them with explosives. After detonation, the shattered rock containing platinum and other metals is transported to the surface for processing. The ore gets crushed, then goes through flotation. That's a process that separates minerals based on how they stick to air bubbles in water. Mills grind the ore down until 60% of the particles pass through 75 micrometers. Then the ground ore gets mixed with water, and collector reagents are added, things like xanthates and dithiophosphates, which make the sulfide minerals containing platinum hydrophobic. Water repelling. Air gets pumped through the mixture, creating millions of tiny bubbles. The hydrophobic particles containing platinum stick to the bubbles and rise to the surface, forming a froth that gets skimmed off. Hydrophilic waste rock particles stay at the bottom. Platinum in Merensky ores is closely tied to base metal sulfide minerals: copper, nickel, and cobalt. The platinum group metals are present either as discrete platinum group minerals included in or attached to the sulfides, or in solid solution with the sulfides. The base metal sulfide minerals in Merensky: pyrrhotite, pentlandite, chalcopyrite, and traces of pyrite. After flotation, the concentrate still contains less than 1% platinum. Now, the concentrate heads to the smelter. It's dried and then heated in electric furnaces to temperatures exceeding 2700 degrees Fahrenheit. Air is blown through the molten metal to oxidize iron and sulfur impurities. Sulfur oxidizes to sulfur dioxide and gets removed as exhaust gas. Iron oxide is removed as phyolite slag. Platinum's melting temperatures are significantly higher than other metals due to the presence of chromium, which makes them incompatible and requires special furnace design. The power capacity of platinum smelting furnaces reaches 19.5 megavolt amperes and 68 megavolt amperes. Energy consumption runs 800 to 850 kilowatt hours per ton of concentrate. Platinum's high melting point means impurities like iron burn off, and the result is a powdery sludge of platinum group metals, rhodium, iridium, ruthenium, and osmium, plus